Good morning, everybody, and welcome to our workshop on the 2018 Residential Energy Code. My name is Carl Little. I'm the Deputy Director here at NCAT. And before we get started, I'd like to go over a few housekeeping matters. First, I'd like to thank our funders. Up on the screen, you'll see our two funders for this that makes this workshop possible. And so a big thanks to Northwestern Energy and the Northwest Energy Efficiency Alliance, or NEA. And then to get your education credits for this workshop, first off, you'll need to attend the entire workshop, and we'll kind of drop in from time to time to make sure you're still there. And then after the workshop is over, we will send a participant list to Tracy Collett at the Bureau of Labor and Industry. And if you will send her an email requesting your certificate at the email address that I have on the screen, and I'll put that up several times during the presentation so you can make sure you have it. And then CC me also on that, so we make sure that everybody gets their certificate. And let's see, also, we want this to be an interactive workshop, and we want your participation. So throughout the workshop, please feel free to ask questions. And there's several ways you can do that. I think Dale will put some time in from time to time to pause for the questions. But on your screen, you have ways to virtually raise your hand. You'll see some. I think if you hover over the top or the bottom, you'll see an option to raise your hand. And if you'll raise your hand, then I'll call on you at the appropriate time to ask your question directly. You'll of course need to unmute your mic, and I think we've made it so that you can unmute your own mic. And then if you want to ask a question by chat function, you can also do that. And I will read those to Dale as they come in. So the workshop is scheduled for about an hour of break time, but we may shorten that. Dale will go over how he's going to do breaks on the presentation. And we hope to get you out of this as quickly as possible and as painlessly as possible. So I think Dale will make it very interesting. So it'll seem like it'll go fast, but we'll try to make things move along. So as you go through the workshop, if you'll just make sure your microphones are on mute after you talk, and feel free to turn your cameras on or off, whichever you'd like. And that's about it, I think. Do you have any questions now? Anybody have any questions? Okay, I will turn the presentation over to my good friend Dale Horton.
Well, greetings. I wish we were in person. I wish this were a live presentation. This is my first experience conducting a live webinar. So if I stumble here and there, please be patient. I was terribly disappointed to hear that there was going to be no canned applause and laughter. I was hoping there would be a little bit more spontaneity there, and just so I wouldn't feel too good about myself, they came up with a chair that lowers me about 6 inches from how tall I actually am. So if I appear terribly short in the images, it's only partly because I am. So let's keep this as informal as possible as the technicians whiz around my head, me wondering what exactly is going on. Okay, all right. So once again, my name's Dale Horton. I've been involved with the energy code in Montana for many years, over 10 years, and have made presentations on the various versions of the energy code beginning back when Montana adopted the 2012 International Energy Conservation Code. And this presentation was originally designed for the State Building Codes Education Conference that was to be held last March. Hopefully next year, we'll be able to meet in person instead of virtually as we are here. Okay, so let me go on to the next slide, hopefully. Okay. So what we're going to try to accomplish here are several things. We're going to try to talk about the significant changes to the 2018 IECC compared to the current code. We're going to put this in, let's say, with an emphasis on performing plan reviews. That was in part because of a response to a DEQ survey from building departments that said they would be interested in a little bit more information about conducting plan reviews for energy-related issues. And then in a Energy Codes working group sponsored by the Montana Building Codes Bureau at the state, there was much discussion about the need for a better understanding of the building science behind the energy code. So, and then towards the end, at the very end, I'll talk very briefly about what was done to the 2021 IECC. So we're talking about adopting the 2018, but the 2021 version has been decided. It'll be published later this year. So I think what I would like to do is propose, and since I'm the one speaking, that probably means this is what's going to happen. I'll try to give you a break at 11 o'clock for 5 minutes at least, then at noon, a 15-minute break, then at 1, a 5-minute break, and then I'm going to try very hard to be done at 2 o'clock. So that's my goal. That's how I will propose to conduct the session so that we get through it as quickly and efficiently as possible. And then I'll entertain questions at the end of each section. And there are, I think, about 12 sections over the 4-hour period. So that's the intention. And Carl has already asked for questions, so I'm going to move on from here. Usually at the beginning of many presentations, you have people talking about themselves to create credibility. And so I would decided to give you a little bit of background about myself. This is the person on the horse on the very right there with the reins. That's my great-grandfather. And this photo was taken in Comanche, Texas. And so you get a sense about my history. This is my great-grandfather. My mother tells me that for all the years she knew him, he never smiled. This photo is taken on the plains in northern Texas, and being in the plains of northern Texas in the 1930s, you didn't potentially have a whole lot to smile about. The rumors are that he chased my grandfather off several times with a shotgun as he was courting my grandmother. This is my grandfather again on a trip when he was 20 from the plains of Texas to Colorado. So now let's move to me and my background. Here I contemplated being a farmer for a number of years, decided country western singing would be a whole lot more productive. My grandmother didn't even think that was a good idea. Then I decided to be a used car salesman. That didn't work out well. So ultimately I became an architect. Here I'm exploring earth shelter construction in the late 70s, which of course was terribly popular back then. And so that's my background. I was an architect and have spent most of my life having to do with energy efficiency, both in commercial and residential buildings. Let's start with a quote by Benjamin Franklin. The quote is, "Don't believe everything you read on the internet just because there's a picture with a quote next to it." And of course, I would encourage skeptical thinking here. And as I go through, there may be a few quotes where I ask you to at least form an opinion on whether you think that's a legitimate quote. So the energy codes originated about the time I graduated from school back in the early 70s, and they were born of the energy crisis or oil crisis when the Middle East oil was shut off. The OPEC countries decided not to ship oil to the United States, and so the oil crisis led to long lines, the lack of gasoline, and it was an unsettling time. And I actually see some similarities between some of the unsettled nature of the early 70s with what we're going through now. I mean, back then we had protests over the Vietnam War. We had violence over the Vietnam War. We had violence over civil rights. Watts had burned in the mid 60s. So I see some scary similarities now to what happened in the early 70s. And later in the 70s, we began to promulgate energy codes, and they were based on basically two things: energy independence for the nation and the cost of energy for individual homeowners and businesses. And so from that, we saw the rise of the model energy codes. Energy codes are often not given the same status as the other family of codes, in part because many people don't believe they have enough to do with life and safety. I think at this point in time, you can argue that with confidence that there are many life safety issues in the energy code, but still when building code departments allot resources, oftentimes the energy code is kind of put in a second-class status because they don't see it as relevant. Some building departments don't see it as relevant as structural and exiting and other life safety issues. Nowadays, even on the national level, when they're deciding energy codes, you have other drivers that are playing a role, such as the most notable global warming or climate change. And so it's a mix of, let's say, drivers that are driving the energy codes that we see today. And regardless of how you want to describe the relevancy or the needs of the energy code, I'm convinced that there are some aspects to building performance that have been driven by the energy code that are very relevant. Comfort, indoor air quality, durability, an attention to how buildings work in building science. These are direct results of the attention to energy efficiency and the energy code. And so the benefits I see in enforcing the energy code are key, and these are the most key in my mind. So the history of the energy codes can be graphed, and I think you can see my arrow. There were significant increases in efficiency back in the 90s. Then there was a plateau. The green line is the residential code. And then in 2009, there was a significant increase in efficiency, near 15%. And then from the 2009 to the 2012 IECC, another 15% improvement. And then in the versions of the IECC that have been promulgated since then, there have been more modest improvements. Montana adopted the 2012 IECC, did not try to adopt the 2015, and is currently in the process of adopting the 2018 IECC, and we'll talk a little bit more about that process. The 2021 IECC has already been finalized. Sometime later in 2020, we hope, the state will adopt the 2018 IECC. So the 2018 model codes that the Montana enforces were already adopted. The state adopted the IBC, the International Building Code, the International Residential Code. mechanical code, the plumbing code, the electrical code, all were adopted and were effective last December, the 7th of December. And jurisdictions then had 90 days to adopt and enforce those codes. So since that time, we've been operating under a 2012 version of the energy code, while the rest of the codes in Montana were operating under the 2018. That's uncomfortable. There are ways the various codes interact, and so it will be an excellent thing to finally adopt the energy code so that you don't have some of the discontinuities you now have in the different versions of the code. The adoption of the energy code has gone at a snail's pace, and the 2018 IEC was published in the fall of 2017. It took a while to finally get listening sessions for the energy code. And then there was a working group sponsored by the state just this last January for different stakeholders to comment on the energy code. And right now, the department has developed its proposed language, essentially the amendments, and has submitted that to the attorneys at the state for legal review. And that's where we are right now. After that review by the state occurs, by the legal experts in the state, then we'll go to the Building Codes Council with its public meetings. Recommendations go back to the department, and the department then issues some final language, which goes through a rules hearing process before it's finally adopted. So we'll be lucky to see the energy code adopted by the end of the year. And let's just say, I'd say it's an understatement that the state has been dragging its feet relative to the energy code. And one of the reasons they did is because in the previous experience in 2014, there were a slew of comments about the residential energy code, a whole bunch. And so this year, or when they decided to update the code, they decided they would treat the residential energy code and commercial energy code differently and put it on a different time track. Well, it turns out there were hardly any comments this time around. And so it's a shame, but the energy code won't be adopted until later this year. And it will be some version of the 2018 IECC. So why is plan review so important when it comes to not just energy-related code issues, but the code in general? Well, it puts the owner and the plan reviewer and the inspectors all on the same footing. The code goes through and requires that the construction documents be submitted for a permit that says the code official must examine the documents and ultimately, if approved, write a stamp or write reviewed for code compliance. So the code is, the IECC is very explicit about the need for plan review. I prepared a plan review checklist, which I will update when the final amendments to the state energy code are developed by the state. And that plan review checklist will be made available by NCAT online. If anybody's interested in what it looks like now, you can email me and I'm happy to send you a copy of the draft. I'd also note that the International Codes Council has a publication that's called the Building Code Plan Review Record. The latest version I saw was the 2015. But if you're interested right now in the most applicable plan review checklist, you can check the ICC library for their plan review record. So to start off, you have to understand that the International Energy Conservation Code is in two parts. The first part is the commercial code. The second part is the residential code. And you have to understand when you're looking at a building, or a portion of a building, whether you apply the residential or the commercial elements to it. And so the thing you have to know is for the commercial definition, they say a commercial building is everything that's not residential. So what's residential? Well, residential are detached single-family dwellings and duplexes. They're apartments, dormitories, and condominiums less than or equal to 3 stories in height. And there's small residential care facilities, R4 is the occupancy label, and they also are less than 3 stories in part. It's important to note that you could potentially have a single family or building or a duplex that was greater than 3 stories in height, but you could not, and still it would still fall under the residential provisions of the IECC. You could not have occupancy R2 or R4 greater than 3 stories and still have it occur, fall under the residential elements. So let's look at a few examples. For example, if you have a 3-story apartment could be apartments, could be residential condominiums, the question is, what part of the energy code, residential or commercial, would you apply to this building? Well, the answer is residential, because it's a qualifying occupancy type, R2, and it's less than 4 stories in height. Well, what if you have a 4-story building and it's all residential? Could be apartments, could be condominiums. What part of the energy code would you apply, commercial or residential? The answer is commercial, because it's over 3 stories in height. Finally, well, I've got a couple more examples. Another one is you've got a 3-story building that has 2 stories of residential above a single story of commercial. And what the code says is that it's a mixed occupancy. You apply the residential provisions to the upper 2 floors, and you apply the commercial provisions to the lower floor. Finally, the 4-story mixed occupancy building, this example, has 3 stories of residential above a single story of commercial. How do you apply the various portions of the code? You apply the entire building is applicable for the commercial provisions. Once you go over 3 stories, it's applicable in the commercial arena, the commercial portion of the energy code. In the commercial portion of the energy code are a number of, they break apart residential from commercial. So in the building envelope, when you're looking at the envelope requirements for the residential portion of a commercial building, the envelope requirements may well be different for the residential than for the commercial. But the entire building, including the residential, is governed by the commercial elements of the code. Any questions? We'll give you about 5 seconds to respond. If you don't respond, we'll move ahead. Okay. This is a question. Did Benjamin Franklin actually say, "Well done is better than well said"? Well, you can form your opinion. Paul, would you raise your hand if you think that Benjamin actually said this? Oh, actually, I was actually asking him to physically raise his hand because I could see him on my screen. And in fact, he did reply. Sorry. There's a raise hand function on the Zoom computer, but Paul and I are of such an age that you would expect Paul to respond like I would have when you asked me to raise my hand. So thanks, Paul. Absolutely right. Benjamin Franklin actually did say, "Well done is better than well said." As I talk for 4 hours today, I'm going to keep thinking about that quote. So the IECC is related to the IRC. Montana adopts the International Residential Code, the IRC, in part. The IRC actually includes mechanical sections. It includes Chapter 11, which is an energy chapter. But the state of Montana, instead of adopting the energy chapter of IRC, it adopts the IEC in its entirety. It just so happens that Chapter 11 of the IRC is exactly the same as the IECC, but the references, if you were to talk about sections and paragraphs and so forth, those are not the same. So Montana adopted the IRC and it adopted the IECC. And there are elements of the IRC that we'll talk about because they relate to energy efficiency. So I'm going to follow a practice of not actually reading off the provisions of the code. For example, I could say that the construction documents need to confirm compliance with the code section R103.1. That would drive me crazy and probably you. So I'm going to leave out the references, but they're here in the presentation if you are interested in where the particular provision came from. So the construction documents shall ascertain whether the construction indicated and described is in accordance with the requirements of the code. So there's specific language that gives the code official the right to require that documents in detail represent the information necessary to judge whether it deserves a building permit. So the construction document requirements are more detailed in the 2008 IECC, and it specifically requires the calling out of these elements. Most of these elements are in the construction documents. Most of these elements you were used to, such as the installation and R values and fenestration, which is of course windows and doors. But it also calls out for specific mechanical systems design criteria and the type, sizes, and efficiencies of mechanical systems. And that's a place where many departments don't see or don't require in construction documents. The way I read the 2018 is that the sizes and design criteria for the mechanical systems are to be provided with the construction documents. And it's also worth noting that the documents are to include air sealing details. And that we'll talk about a little bit more, but that's quite a bit of detail. And obviously the sophistication of the building community in any given building department will have an effect on this. But I guess the critical thing here is the 2018 IECC is more explicit and detailed in terms of its construction document requirements. The ICC, the International Codes Council, has a publication that would be useful if you're interested in helping understand how particular provisions are interpreted. The code and commentary is available. I think it's around $70, but it's extremely useful if you've got questions and just almost necessary if you're a code official. For example, in the code and commentary, it says explicitly that you cannot just a plans set of documents that are submitted for a permit can't say something general like all insulation levels will comply with the 2018 IECC. Well, maybe that would be simple from a builder or designer's point of view, but it doesn't fly. And the code and commentary provides even greater explanation than the provisions themselves about what's actually required in the code provisions. The IECC specifically says that the documents must be drawn to scale in sufficient clarity to indicate the location, nature, and extent of the work proposed. And it's an education and ongoing process for building departments to educate builders and designers about what needs to be submitted for a permit. The other change in the IECC that's worth noting is the inspections that are to be carried out by the inspector. There was some language, general language about inspection in previous versions, but the 2018 goes into much more detail about what's to be inspected and what's to be included in the various inspections. I won't go through and read these in detail, but let's just say that when the building department begins to enforce the 2018, it's probably worth reading this section in R105 about the different inspection criteria. So another important addition to the code is a statement that says that the code official is authorized to accept reports of approved third-party inspection agencies. And this was added particularly to deal with the energy rating index, an additional compliance approach that's added in the 2018 compared to the 2012 current code. And so what this says is that explicitly the building department can accept inspection reports from approved third parties. There's a couple different definitions that are changed in the 2018. One of them has to do with what's conditioned space. This is important for several reasons. The first one that came to my mind is when you're setting the duct tightness limits, which we'll talk about later, you have to know how many conditioned square feet of floor area there is. And so you have to understand whether the space is conditioned or not. And the definition says it's not only its conditions, of course, if it's directly conditioned, but it's also considered conditioned space if one of three things occur. First, if there are uninsulated ducts or piping inside the space, then it's conditioned. If it's separated by an uninsulated wall, then it's considered conditioned. Or if there are openings between the space in question, such as a basement, and the directly conditioned space. So the conditioned space is the area surrounded by a thermal envelope and is heated directly or indirectly. And that helps explain how you calculate conditioned space, which you need to do, for example, when you're deciding how much air leakage is allowable in the duct system. Questions?
Apparently the raise hand function's not working. So if you have a question, just go ahead and unmute yourself and ask the question, or send a chat message.
Now I can see Mark, Paul, and Hal on the phone or on my screen. So you guys can actually raise your hand if you want to. I don't know how this works and why you were the specially chosen three that I get to observe. All right, we'll move along, but please feel free to interrupt anytime you'd like. Okay, so here's a question. This is a quote that you commonly see attributed to Benjamin Franklin. It's, "God made beer because he loves us and wants us to be happy." So, Paul, do you think that was a legitimate Ben Franklin quote? He's shaking his head. And I think he's on top of it. In fact, the actual quote is, "In wine there is wisdom, in beer there is freedom, in water there is bacteria." That is a legitimate Ben Franklin quote. And the question is, who in the hell cares? And then who figures this out? There's actually a Ben Franklin Institute in Philadelphia, of course, who decides whether these are legitimate Ben Franklin quotes. So the Energy Code has a number of compliance options or compliance approaches. Sometimes we call them a compliance paths. There's a prescriptive path, which is by far the most common. There's a performance path, which has been in the code for years now. And then in the 2015 and 2018, there's a new path called the Energy Rating Index. The key thing with all these compliance paths is there's a set of mandatory provisions that have to be complied with regardless of the compliance path that's selected. The prescriptive path is by far the used most of the time, and there's actually different approaches or different ways to use the prescriptive path. One is a table that everybody's used to. that says here, this is the minimum R value or U value for a building component. And that's the insulation fenestration table. And that's what is used most of the time. Then there's a U factor alternative approach, where instead of using R values, you use U factors. And it's a different approach. It has a different calculation, but it's another alternative. And then there's also a trade-off alternative. And in a trade-off alternative, you can, let's say you've got very efficient windows and you want to skimp on insulation somewhere else in the building. Well, you can trade off the energy efficiency of those choices with the trade-off alternative. And the trade-off alternative is easily accomplished using software called REScheck, which is Department of Energy software that I'll also talk about in a minute. So REScheck, this software that you can use to, in a orderly way, go through the code requirements, especially the envelope requirements, if you're interested in trading off alternatives. And the key thing to understand for 2018 is that it won't be it doesn't include the Montana amendments. And this has been true of the past. So you can go online and use REScheck, and it's still a good idea to do that. But just understand that it's not a Montana version. It's the unamended IECC that REScheck is testing. So
Dale, real quick, they have a question. I think it's on your previous section. And the question is from Lloyd. Does the floor area include the area of the insulated walls?
It's, yes, it's to the outside of the insulated area. So only a sadistic person would require you to calculate the area based on the interior wall size. So it's to the exterior. Okay, so this slide just emphasizes the fact that all these performance paths still are subject to the mandatory provisions. So RESchecks, it's probably worth talking about REScheck for a minute. It's used fairly widely in the state. I've seen, especially in some of the larger jurisdictions, numbers of REScheck submittals along with the construction documents for a permit, and I highly recommend it. The 2018 does create a slightly different dilemma in that you have to use the online version. When DOE created and Department of Energy maintains the software, there was an option to download it on your computer, and there was an option to do it online. With the 2018, you will only be able to use the online version. So if you want to use REScheck once the 2018 is adopted, then you have to use their online version. You can go to the URL that's shown at the bottom of this screen, the energycodes.gov, and either download the REScheck that would be used for the current code based on the 2012, or you can use the software online for analysis in the future on the 2018. So there are two versions. I've mentioned both for the online version and the downloadable version. The 2018 IECC will be available only on the downloadable or web version. This software does have, supposedly has a performance-based option, but it's a very weak performance-based option that doesn't allow trade-offs for HVAC, building tightness, and so forth. So the ERI provides much greater flexibility, and REScheck's doesn't have the ERI calculation capability. And once again, REScheck is not customized for the Montana amendments. So once 2018 code is adopted, if you want to get a pass, you'll have to meet the unamended version of the 2018 IECC. So this is kind of what it looks like, the web version, the online version. You can create a number of projects. They'll be stored online for you when you enter them and work on them again. You have to tell it, the software, what energy code you're going to use, and then you introduce the basic characteristics of the building, the site, the conditioned floor area, the orientation of the walls, and you go through a series of building components, adding areas and the characteristics, R values, U factors for the building components. You go through that process and it ultimately will give you a score of passing or not. And it will also allow you to print out a checklist of what it believes is a set of energy code provisions that are applicable to your project. And it also provides building code officials an inspection checklist. A couple of things the inspection checklist doesn't do, though, is it doesn't autofill with what the project calls for in terms of R values, U factors, and so forth, which would be a huge improvement. It's also a little limited. It doesn't cover all of the requirements. Checklists are more art than science, I think. I've looked at many, many checklists for the energy code, for plan reviews, and everybody has a little different philosophy about what should go into a checklist. But still, REScheck is a really wonderful tool, and I'd highly recommend you think about it for use if you're submitting drawings, or if you're a code official, in encouraging people that are submitting drawings to use. So we're going to talk a little bit about the calculations involved with doing plan reviews. And the calculations, you usually don't think of needing calculations with prescriptive compliance approach. You usually don't. But if you do such things as area weighted calculations, then you'd be using some calculations. Once you get into using the prescriptive envelope characteristics of either the UA alternative or using REScheck, then you're doing quite a few calculations having to do with areas and coming up with the R values, U factors for various components. And then when you get into performance and ERI, you've got numerous calculations, at least the modeler has to, the person that's actually inputting into the simulations have to be conscious of. And as a code official, you would want to at least be able to understand that software so that you can do some sort of quick checks to make sure that what's entered in the software is actually in the construction documents. A few years ago, I did some work looking at different code departments and went through just randomly and was looking at REScheck submittal reports versus the actual plans, and found numbers of areas where they didn't disagree. So a code official, even though you get a nice, neat report, as you do with REScheck or with the other software used for modeling in performance or ERI, it still behooves a code official to do some very general checking to make sure what's on the it has been entered into the software is actually what's on the documents. So without going into gruesome detail, there's a calculation that allows you to do area weighted calculations. When would you do this? Well, let's say you had some of your windows that didn't meet the prescriptive U value requirement, but then a lot of your other windows did in fact surpass the energy efficiency required for windows. You could do an area weighted calculation, which is allowed even under the prescriptive path, to make sure that the average R value or U factor met the criteria. So you could, in fact, have some windows in your project that didn't meet the prescriptive requirement, as long as you had other windows that made up for it. And this is the formula you would use. It's just an area fraction times the U factor, and you can do that for as many different areas as you want. This is an example of a calculation where you're calculating the area weighted U factor for the ceiling, since it has a hatch area that's much more poorly insulated than the rest of the roof. I'm not going to go through it in detail, but the slide gives you a fairly simple way of being able to calculate what the weighted value is. Instead of ignoring the roof hatch, well, of course, if the roof hatch met the requirement for ceiling insulation, you wouldn't have to do the calculation. But for some reason, some area of the ceiling failed to meet the requirement, you could do this U factor calculation to see if on average the whole thing met the entire ceiling met the requirement. The U factor alternative uses a different table in the code, and that code, instead of including R values, it's just full of U factors. And so U factors are just the inverse of R value. But the big thing, if you were to use the U factor alternative, is that you can't use just the nominal insulation characteristics. When you're looking at the basic prescriptive table and it requires R49 in the ceilings, then it's just saying that the nominal insulation has to be R49. It's not asking if there are bottom cords of trusses that are in place. If it's looking at wall R values, it's not asking you about framing percentages. It's not asking you about the insulation characteristics of the sheathing. It's just asking simply for the nominal R value. However, with the U factor alternative, you have to include all the components of the building assembly. And that includes an inside and outside air film, the sheathing on the inside and the outside, any air spaces that might exist, plus the effect of having a certain amount of framing and a certain amount of insulation. And so you do a calculation that's using basically the same approach, where you turn all the R value element, you add the R value elements for the different areas. If you had more than 2 different conditions, let's say you had 3 or 4, you would have multiple columns and have to, again, add up the R values, convert the R values to U factors, plug the U factors plus their area fractions into this formula to calculate the area weighted U factor. It's that area weighted U factor you then compare against the U factor table that's in the book. And why would you ever do this? Well, one reason is that it tends to be a little more lenient. And if you had a situation where you had a bunch of different wall types and you did an area weighted and just used the R value approach, you might fail. If you turn around and use this approach where you consider all of the elements of the assembly, it might pass. But again, it's a complication that is there to offer flexibility, but it can be a little bit confusing. The energy certificate is a requirement, and the energy certificate that's shown in this slide is available from Department of Environmental Quality. Keep picking on Paul, but he's the person you'd probably talk to at Montana Department of Environmental Quality about getting copies of these labels. These labels are designed to include the information as required by the IECC, and importantly, it includes an area for the builder to sign the certificate at the bottom. In the state of Montana, the energy code is applicable to every single residential building that's built anywhere in the state. We know that some areas of the state don't have enforcement of the residential energy code unless a local jurisdiction has chosen to adopt the residential energy code and enforce it, then you don't have enforcement of the building and energy code in rural areas. You do have enforcement of the electrical code and the plumbing code, but not the building code and the energy code. And yet it is very explicit that every single building, residential building, regardless of where it's built, anywhere in the most remotest part of the state, is technically, legally required to meet the energy code. And the state law creates a self-certification option, and that self-certification option says that builders who build outside of local jurisdictions have to provide the owner of the building with a written statement that it applies, that the building complies with the energy code. And a builder, if they sign this label and affix it to the breaker panel in the house as it's supposed to be, where it's supposed to be placed, then that is sufficient to meet that state requirement. There's still areas of the state who believe they're not applicable to the energy code because the energy code and they don't see an inspector that's looking specifically for energy code and building code elements, but that's not true. It's applied to every building. So there are two exceptions to the application of the thermal building envelope requirements. One is if the heating system designed for the space conditioning system designed for the building has a very, very low amount, its capacity is very small. And so the code provides a metric for when so little heat is supplied to a building that you don't have to apply the thermal requirements. And of course, no conditioned space, if there is no conditioning in the space, then you don't have to apply the code. Even though you may not have to apply the thermal requirements of the energy code to an unconditioned building or a very small heating system building, you still have to apply all of the other relevant codes having to do, let's say there was the lighting. The lighting still has to apply to the building, even if the thermal envelope characteristics do not. In a new provision in the 2018 IECC, it provides an exception for the ICC standard 400. And this is a log homes standard that's existed for many years, but this is the first version of the IECC where it's inherently a part of the code unless it's amended out. I have no reason to believe it will be amended out. And so what it will say is that if you're doing a log home, then instead of paying attention to the thermal envelope requirements of the IECC, you can meet the thermal requirements of the ICC 400. ICC 400 was developed over 20 years ago by a group of associations along with the National Home Builders Association. So it's kind of a consensus document that its purpose is to provide consideration for how the thermal mass of log buildings behaves differently from an energy point of view than light frame construction. And so it has lots of different information about moisture content, structural design, and so forth. But what's key is that if it meets one of the three prescriptive, one of the three compliance methods for thermal envelope, then that satisfies the IECC requirement. So, and this is just a kind of a repeat slide. It notes the section in the IECC that refers to the ICC 400, and it notes the section in ICC 400 that refers back to the IECC. So just really quickly as an example of what it looks like, it's dependent largely in the prescriptive approach, which is the only one I even pretend to barely understand. It's dependent on the nature of the logs and the thickness of the logs. And then it has the insulation values for other building characteristics. So depending on the type of log it is, and let's just pick an example. Let's assume it's a lodgepole pine. Then it would have a specific gravity of 0.41. That's less than 0.5. So you would, the walls would qualify as long as the average width of the wall was at least 5 inches. If it was larch, which has a higher specific gravity, then the average wall thickness of logs, of all the logs, would have to be over 7 inches. So it's not maximum thickness, it's average thickness. So if you meet that requirement, then your requirements for windows is less than what it would be if it were the 2018, which goes to 0.30 for U factor in fenestration. It's a little more lenient on skylight compared to 0.55. The ceiling U factor is the same. The wall is slightly different. It's if you have sections of frame. This is if you have sections of frame wall interspersed with log walls. Its floor R value is the same. Basement, interestingly enough, the slab R value is R15 instead of R10 as it would be for frame buildings. But if you meet these criteria, then you've satisfied the ICC, the ICC 400 thermal requirements, and that satisfies, therefore, the thermal requirements of the ICC in total. So there's a couple questions that always come back is, do you still have to test the building envelope for airtightness? And the answer is yes, and it has to do with the provisions that the exemption for the ICC 400 apply to. You still have to do an airtightness test, blower door test, and then the question sometimes comes up about a vapor retarder. There's information, provisions in the IRC that says you don't need a vapor retarder if essentially the construction of the wall itself is not going to be damaged by moisture entering the wall. And so you, the way I interpret it and the way I've seen it interpreted is no vapor retarders requirement on a wood wall. So,
Dale?
Yeah.
We have a question is whether ICC has been adopted by Montana at this time.
Okay, the ICC, well, okay, let me go back to it this way. The current energy code in Montana is the 2012 IECC. So the IECC that Montana is now using is a slightly amended version of the 2012 IECC. Montana is in the process of adopting the 2018 IECC. That will hopefully be culminated later this year. And so the ICC 400 option won't be in place until the state adopts the 2018 IECC later this year. In the past, many, many years ago, over 10 years ago, the state considered adopting ICC 400, but finally did not. So the ICC 400 is only going to be applicable once the state adopts the 2018, given there's no amendments that I'm not aware of. Hope that helps. Okay. Okay, that was, any other questions? Okay, it's 11 o'clock, so let's take a 5-minute break. I'll come back and start promptly at 11:05. Get started again. And I apologize, but for some reason, evidently, the participants are not seeing a raise hand function on their screens. So please feel free to break in at any time, and then the type in chat option, if you have a question or comment, is also should be available to you there. So let's charge ahead. So this is a question for Paul. I'm picking on Paul Cheetah with Montana Department of Environmental Quality, just because I can. So is this something Ben Franklin said? Science is bending over backwards to prove ourselves wrong. He's shaking his head. And once again, Paul is spot on. That was actually Richard Feynman, the physicist, who said science is bending over backwards to prove ourselves wrong. You know, the thing I like about science is it's humble. Individual scientists aren't necessarily humble, but science is humble in that it's always trying to prove itself wrong. It's always, science is basic, all science is what we know now, our best guess right now. It's always looking for better understanding, better answers that better fit the circumstances. And building science largely did not exist before people began to figure out how to make buildings more energy efficient. And I just think it's fun, but I'm kind of a nerd anyway. So building science is what we now think about buildings. And yes, these are my relatives back in Texas in the late 1800s. And I don't even know exactly who they are, but I thought I'd at least show you the pictures. And these were amazing buildings. They never had problems with moisture in building cavities. And the reason is that the building cavities were so leaky that air just passed through them almost through a sieve. And it's only when we began to insulate and tighten our buildings to save energy and to improve durability that we had to begin to understand how in the world buildings work. And that's largely physics. So let's talk a little bit about building science. The basics of how heat moves in a building includes three heat transfer mechanisms: conduction, convection, and radiation. If you look at an empty cavity, a wall cavity with no insulation, it can illustrate all three transfer mechanisms. Conduction is the transfer of heat through solid materials. Convection is the transfer of heat by the movement of molecules, in this case air molecules circulating. And then radiation, which is a transfer by electromagnetic radiation based on a temperature difference, gap, and a line of sight. And so in this example, you have conduction through the solid framing members. You've got air movement within the cavity based on the density of the air. And then you have radiation from the warm side to the cool side of the wall cavity. If, on the other hand, you fill that cavity with a non-air permeable insulation, what have you got? You've got conduction only. You've eliminated the line of sight and gap necessary for radiation. You've eliminated the ability for air to move and circulate. And so in this example, heat is moving from hot to cold, as it always does, according to physics. And in this instance, the single membrane or mechanism used is conduction. So back to a little bit of math. R values are a measure of thermal resistance. U factors, a measure of heat transfer. You're probably familiar with the fact that they're inverse. So R equals 1 over the U factor. U factor is equal to 1 over R. The key thing to understand is R values are additive. U factors are not. You can convert U factors to R values and then add them. But if you try to add U values, you're going to get garbage. So the R value series of components can be added. If you know you've got R2 and an R3 and an R4, you can sum them. And if you divide that by the if you look at the inverse of the R value, then you can calculate the U factor. Boy, I butchered that. Let's go back to it and make it simple. R value goes 1 over the U factor. U factor is equal to 1 over the R value. Okay, R2 plus R1 is equal to R total. U2 plus U1 is equal to garbage. And then I'll remind you of that relationship. It's important to keep those in mind when you're evaluating energy efficiency options in the thermal envelope. Different components have different R values. And here's a chart that has some of the most common insulating materials and the R values. Just because you have a general characteristic, a type of foam, for example, you don't know what the actual R value unless you know exactly what kind of foam it is, whether it's expanded polystyrene or extruded polystyrene. And often you don't even know the R value, what the R value is, until you get the information from the manufacturer. So when you get into some of the foams and some of the insulation materials, you not only have to know the characteristic of the material, you have to know its density in order to know what the actual R value is. So to know the nominal R value doesn't tell you the whole story in terms of what you're getting out of a building component. For example, if you look at a wall and fiberglass bats, let's assume the bat is an R19 bat, all right? But even in best practice, when put into a wall, the effective R value of the whole wall is about R14. And then if you have a poorly or typically installed fiberglass insulated wall, it can be as poor as effectively R11. And then of course, a steel stud wall is different because of the conduction of the steel. So the story that has to be told about the effectiveness of insulation isn't as simple as talking about the R value. This table looks at the effectiveness of R values and includes the installation quality of the insulation. It's not in the code yet, I think it'll be eventually, is that when you're doing like a HERS rating or a energy rating index analysis, you have to evaluate whether the insulation is put in as grade 1, 2, or 3. And then obviously there's a difference if you've got exterior rigid insulation. The IECC has since 2012 said that in this zone you should have a rigid insulation on the outside of all walls. But Montana has amended that provision in the IECC to not require that continuous insulation. The big difference in energy use between these various walls are that the upper set of walls have an inch of rigid insulation, while the lower set of walls do not. The other factors that are important is the percentage of framing. So if you have advanced framing, 24-inch on-center studs and so forth, you've got lower framing percentage than if you have a more standard 16-inch on-center construction. And the reason I put this graph in is just to emphasize the fact that not all walls are made the same. You have to look at the different characteristics of the walls in order to understand how well they're going to perform over time. The other basic factor to understand when you're talking about insulation is that there are diminishing returns with insulation. So you reduce heat loss by 50% going from R1 to R2. But if you are going from R50 to R51, you're reducing heat loss by much less than 1%. And the lesson here is somewhere when you're designing walls, ceilings, and so forth, it becomes less efficient, less cost effective to install more insulation. And I'm not going to tell you what the perfect values are, but it's the nature of insulation to have diminishing values. The other thing to consider when you're talking about walls is the thermal gradients that are created. You don't have to pay too much attention to all these complicated lines, but what this is attempting to show is that the effective R value of walls as you add insulation is lower, not just the effect of the insulation, but the effect of the whole wall itself. The other consideration that we care about is the temperature on the inside of the exterior sheathing. We care about it because if the temperature gets too cold and there is moisture introduced into the wall cavity, you can have condensation. So by adding insulation to the exterior of the building, you can increase the temperature of the inside face of the exterior sheathing, thereby reducing the potential for condensation on that surface. And that's to try to explain why does the National Model Code suggest you should have continuous insulation. It's for two reasons primarily. One, it's greater R value, an effective R value for the wall, and because it raises the temperature of the inside face of the exterior sheathing. Window basics, you've got solar heat that's transmitted through the glass. Some of that heat is absorbed by the glass and re-radiated in either direction. Then you've got the re-radiation of heat from the inside out through the glazing. And then you've got heat loss that occurs through the various components of the building, the window assembly, the edging at the glazing, and then the frame itself. And then you've got air leakage that occurs through the operable elements of the glazing. And then let's talk about air pressure. Air pressure is a little hard to get a grasp on sometimes because you can't see it. This is a slide that actually allows you to see air pressure. What's happening in this building is you've got warm, moist air rising in the building, creating greater pressure, positive pressure higher in the building, and negative pressure lower in the building. Why does a plan reviewer or a designer or a builder care about this? Well, nowadays, when we're doing building tightening, testing with blower doors, we're testing ducts, and we're considering the pressure differentials within buildings. All of a sudden, folks that are involved with the building industry are being confronted with issues that have to do with air pressure. Stack effect is a term used for the pressure that's created higher in the building due to the positive pressure of less dense warm air rising, more dense cooler air following, which creates exfiltration higher in the walls and infiltration lower in the walls. Wind can have an effect on the pressure in a building. It can exert positive pressures on the windward side, and where you have infiltration, and then the wind itself blowing over the building can create negative pressures outside the leeward side, and you can have exfiltration on that side. So wind-driven pressures can drive pressures in a building. I throw this slide in just to try to create some analogies to perhaps help folks who are new to the issues of energy to better understand what's going on. Obviously, these two pieces of clothing do two different things. The insulation gives you warmth on a still cold day. You can wear a fleece jacket, which is very air porous, and be very comfortable. The minute the wind starts blowing, this fleece jacket alone is no longer comfortable, and you naturally provide a wind shell on the outside to stop the wind. And in building parlance, we call the detraction of the negative impact on insulating value wind washing. In other words, wind can, in an air porous material, reduce its insulating effect. Another attempt at an analogy has to do with boots. And you could ask yourself, which of these boots would you choose to hike in if it was minus 30 degrees? Well, the packs we're used to packs have this more or less air impermeable exterior, and it has a largely wool felt interior. And if you've ever done this, you realize that if you're out walking in very cold temperatures and you're walking vigorously, your feet are going to sweat a lot. And what happens is you can wet the felt to the point where its insulation value can be seriously depleted. And so I lived in Alaska for a few years when I was younger, and we would literally put plastic bags over our socks before we put our feet into the packs when we were going to go walking, for a bunch of hours, because we knew where our feet were going to sweat. We didn't want to detract from the insulation value in the liners, so we would contain all the moisture from the sweating within that plastic bag and in our socks, which got very wet and very smelly. The other option is we could have worn these bunny boots. These bunny boots were created in the Korean War for cold weather trekking, and it's basically encasing a felt insulation within plastic on both sides. And so here you didn't have to wear your plastic bag because you could put on your socks, put your socks in the bunny boot and Mickey Mouse boots, and sure enough, your socks and feet would be wet as can be, but at least you wouldn't have detracted or minimized the insulation value. I'll take comments after the presentation as to whether these analogies make any sense, but my point is that we care about what happens to the moisture within a building cavity, just like we should care about what happens to moisture when we're choosing footwear. And so to test your patience, I thought I'd give you another little analogy. Here's a lodge in Alaska where I spent some time, and I was told, I basically was caretaker for the winter, and I was told to turn this 12 by 12 cabin into someplace to spend an Alaska winter. And he handed me a bunch of R11 bad insulation with paper faces. So I put R11 on the walls and on the ceiling. The ceiling had no covering, and I had plywood to cover the walls. And everything worked fairly well until it began to rain inside the building in the springtime, because all winter the moisture we created from breathing and cooking moved up through the insulation and condensed on the metal roof and continued to build up a huge ice lens on the underside of the metal roof all winter. So in March, when the weather became a little bit more moderate, it started to raining. And so I did then what I should have done at the very beginning. If I had put a sealed plastic polyethylene barrier up underneath the insulation to begin with, I wouldn't have had the problem that we did. And I wound up having to use the polyethylene to catch the condensation that was melting from the roof and catch it in the coffee cans. I'm very proud of the double pane windows I handmade with electrical tape and a little bit of desiccant. This was back in 1981. And then I was also proud of these mystery mirrors. This mirror I put on here because we only had north windows and we wanted to be able to see the sun. So I put a mirror out to reflect the south and get a look at the sun once in a while from inside the cabin. And this mirror here was because we had a grizzly bear that was wandering around the compound, and I wanted to be able to see whether there was a grizzly hiding around the corner. So if you're not convinced that there is water vapor in the air, then you can set a glass of ice water out on the table, and sure enough, you'll get condensation on that glass of ice water, because the temperature of the surface of the glass is below the dew point temperature, which is the temperature at which you get condensation. So all air has moisture in the form of water vapor. Some has more than others. One way to avoid having that condensation is insulation. If you insulate the cold beverage, then you can raise the temperature of that surface to the point where you won't have condensation. Water is introduced into a house many different ways: breathing, showers, cooking, and so forth. And it's pretty astounding, especially when you get children in the family, how much water is introduced into the building. Indoor humidity is important. If it's too dry, then it exacerbates some health conditions. If it's too wet, then you can have mold and dust mites and other problems. EPA says that between 30 and 50% relative humidity is about right for homes. And actually, that's about right for homes from the standpoint of the integrity of the building itself. If you get relative humidities much above 50%, you're going to almost inevitably have issues with condensation and mold. The trouble is that builders and designers can't entirely control what relative humidity occurs in a building. And you can introduce some design elements such as dehumidistats and ventilation and so forth that can help limit very high relative humidity. And of course, in some environments, you both dehumidify and humidify based on the health needs of the occupants. But 30 to 50% seems to be the sweet spot in terms of relative humidity. Air moves from areas of high air pressure to areas of low air pressure, and air moves based on the size of the opening and the air pressure differential. Water vapor is smaller in terms of molecule size, and so wherever air can go, water molecules will follow. Water vapor is moved through two different mechanisms. One's diffusion and one's air transport. But air transport, where the actual air molecules are moving through leaks and holes, are way more significant by an order of magnitude than with diffusion. This is important as we talk about vapor retarders and air barriers. Houses have numbers of air leaks. We're familiar with this kind of diagram, I think, where you've got leaks every time. You have potential leaks everywhere there's a junction or a penetration, or where you have movable objects such as doors and windows. So all of these elements need to be dealt with if we're going to create a tight envelope, and that's what we're trying to do according to code. So if you have a house with the same relative humidity, meaning you produce the same, let me say this a different way. If you're producing the same amount of moisture in a house and then tighten the building envelope, the size of these arrows is supposed to indicate how much air is leaking through the building envelope. If you shut down and reduce the amount of exfiltration, then the relative humidity will go up because you've got less air leakage, therefore less movement of water vapor from the inside to the outside of the building. Another way of dealing with water vapor in a building is through exhausting it. And so even though you have the same amount of moisture being produced, you won't see the same relative humidity if you exhaust the air. And essentially the requirements for exhaust ventilation are dealing with this reality here. So the codes address both a continuous air barrier and a continuous vapor retarder. The codes no longer use the term vapor barrier. We'll talk a little bit more about that. So the word vapor barrier doesn't exist in either the IRC or the IECC. The continuous air barrier is addressed in the Energy Code, the IECC. The vapor retarder is addressed in the IRC. I talk about it here because I think you can hardly talk about how you construct a wall for energy efficiency and for building integrity without talking about both the vapor retarder and the air barrier. So moisture in cavities is a problem. And we've seen damage done along the rim joist in the attic and condensation at the windows because of uh, the lack of air barrier and high humidity in the building. And that can lead to mold and rot within the building cavity. So mold can be dealt with in really only one way, by controlling moisture. You can't eliminate mold spores, you can't burn them out, and you can't really eliminate the nutrient sources, which are water and wood. So controlling moisture is how you deal with mold. This is one of my favorite all-time slides, and it looks at condensation in windows. Builders are forever, at least in my career, asking why they have condensation problems in the house when they first move in, and their clients are very unhappy when they see condensation on their windows. And I say, well, it's all science. And this, if I were a builder, I'd hand this graph out to each person I sold a house to, because what it says is the presence of condensation on windows is directly related to three factors: the R value of the window, the relative humidity of the indoor air, and the outdoor temperature. For example, if you've got double glazed low E glass, like most of our houses do today, you will see condensation on the glass if it's minus 20 degrees outside and 50% relative humidity. So the presence of condensation on glazing is a product of those three factors. And you can't eliminate it entirely unless you control the relative humidity and you put in very efficient windows. So exterior sheathing, exterior walls are kind of one of the huge challenges in trying to eliminate condensation. Back before we insulated walls, we would have temperatures on the inside of the exterior sheathing in the nature of about 55 degrees, which wasn't cold enough to create condensation. If we add insulation to that space, we reduce the temperature of that exterior sheathing face, and that's when we began to see condensation. And so adding insulation to the wall required us to minimize the amount of moisture that gets into that wall, because then we'll have condensation. So before we had what I call an enlightened wall, we had movement of water through the sheetrock by diffusion. We had movement by air transport through penetrations and at the top and bottom plates. And then we would have condensation of that moisture as it easily penetrated the air permeable insulation, such as fiberglass. It would condense on the outside sheathing and create problems. And this was occurring considerably in the 1980s. On the outside of the wall, we had bulk moisture that would sometimes and often penetrate the cladding or siding that would then wet the exterior sheathing. And we had wind washing that would be able to move through the leaks in the exterior wall and would reduce the insulation value of the air permeable insulation. So we had all these things happening in the pre-Enlightenment wall. We had diffusion, we had air transport, moisture moving in from the inside, and we had moisture moving in from the outside from rain, and we had wind that was detracting from the insulation value of the wall. The enhanced wall that we're now talking about and we're commonly seeing has a vapor vapor retarder. I'm trying so hard not to say vapor barrier that it's slowing me down. We've got a vapor retarder on the inside, and we have a sealed air barrier. By having a vapor retarder, we eliminate the possibility of excessive water vapor movement by diffusion, which is less important than the air barrier, where we've eliminated water vapor moving into the cavity by air transport. On the outside, we've introduced a water-resistant barrier, which is required by code. Some designers include a drainage plane gap. It's not a code requirement. And then some code elements require exterior insulation. And if taped, that exterior insulation can act as the water-resistant barrier. So we've got vapor retarder, we've got an air barrier, we've got the water-resistant barrier, which is often house wrap. All those elements have combined to give us a better performing and code compliant wall. So here's a couple of questions for you. Does the code allow the air barrier and water and vapor retarder to be the same component? Think for a minute, and the answer of course is yes, because there are times, depending on what you're doing, that the vapor retarder and the air barrier are the same material. For example, if you're using polyethylene. So yes, indeed, the vapor barrier and the vapor retarder and the air barrier can be the same material. Does the code allow 2 air barriers? And the answer is sure. And is it a good idea? And the answer is it depends. And the reason it depends is that it depends on the type of air barrier and whether the air barrier is air permeable. We'll talk about that in a minute. Does the code allow 2 vapor retarders? The answer is yes, if you want to. The code doesn't say you can't, but is it a good idea? And once again, it depends on the air permeability of the vapor retarder. Does the IEC require house wrap? No, but the IRC does require, spelled wrong, a water-resistant barrier. And so the water-resistant barrier doesn't have to be house wrap. They actually allow lapped 15-pound felt to act as a water-resistant barrier too. But it does have to have a water-resistant barrier. Questions? Gone? Okay, what are the envelope code requirements? The envelope code requirements for the thermal envelope for the prescriptive path are shown in this table. And so windows and doors in the 2018 go from 0.32, which is the current requirement, to 0.30, unless for some reason the state chooses to adopt the amendments suggested by the Montana Building Industry Association. The Montana Building Industry Association proposed that we take the entire prescriptive table included in the IECC and revert back to the 2009 version. So I don't think that's going to happen, but that's what the Montana Building Industry Association proposed. What I think will happen is that we will see a slightly more efficient requirement for windows. There have been studies in Montana suggest that the average U value of windows now being installed is already better than the 0.30. The skylight ceiling requirements are the same. The wood frame wall requirements, I believe, will stay the same, which are in fact different than the actual IECC requirements. But I think that we'll stay with the R21 minimum, not requiring continuous insulation. The other elements of the prescriptive table aren't changed from the current code. The window U factor, the U factor in a window, you have to have one of these National Fenestration Rating Council labels in order for it to count. So a builder is well advised to leave these labels on so a building inspector can actually tell what the U factor is. And of course, the U factor, 0.30 is what it will be for the 2018 IECC. The label itself actually has some other interesting features that are non-code issues in our climate. The solar heat gain coefficient is how much solar heat passes through a wall. In many of the climates, this is mandated by the code. It's not mandated in Montana, so there's no solar heat gain coefficient. The lower the solar heat gain coefficient, the better the window is at rejecting heat, and the values are from 1 to 0. And then visible transmittance is a characteristic that architects might use if they were going to provide daylighting for a building. It's a measure of how much of the sun's light in the visible wavelength can pass through the window. The reality is if a window doesn't have one of those labels, according to the code, you then have to use a set of default values that are contained in Section 3 of the residential IECC. And I put together this table, which basically says that based on different types of window frame, that if you've got the label that says 0.30, that's fine. But if not, and it's a double pane glass, you have to use 0.55. So if you see a window on the site during inspection has no labels and it's double pane, you're to assume that it's 0.55. So obviously there's a huge incentive for builders to provide evidence to the building department of the U value of the windows and doors. Doors also must meet the same fenestration requirement as windows. Typically, solid core doors are 0.2, 0.5. Wood panel doors are 1.75. Insulated panel doors are in the neighborhood of R5 to 7, which is a U factor of 0.2 to 0.14. So you're using the same, in the 2018, you'll be using the same 0.30 U factor when deciding if a door meets the code requirements. So there are no solar heat gain coefficient requirements for Montana in the code for our zone. You may use area weighted U factors for a given component, still using the prescriptive table. There's a provision that allows you 15 square feet of fenestration that does not meet the U factor requirements. And there's an opaque door allowance of up to 24 square feet that is exempted from the U factor requirement. So you've got a couple of these exemptions which do allow you to skirt the code if necessary for small window and door areas. Steel frames, I won't go into a lot in great detail, but steel framed building assemblies are included in the code, and it basically says you have to meet the R requirement of the wood frame wall. So if you've got to meet the R21 requirement and you've got 16-inch on center steel joists, then here's how you can meet the R21 requirement. You can have R14.6 continuous, or on the other hand, you can have an R21 in the cavity of the steel frame wall, but you have to have an R8.1 rigid in addition. So this is not something we see a lot of, but you might see it, especially in multifamily housing, if someone were to try to use a metal frame instead of wood frame for the exterior wall. Then you'd be applying this provision in the code. So R38 is allowed for ceiling, R49 is the minimum, but R38 is allowed if the depth of the insulation or the total R value is maintained out over the exterior walls. There's a requirement in the code that you have to have an eave baffle if you have air permeable insulation, and this is to allow air to vent through the 2-inch minimum space and into the attic in order to provide ventilation and the removal of any water vapor that might accumulate in the attic. It also is there to try to reduce the temperature on the underside of the sheathing to minimize ice dams. And so you are required to have this venting if it's air permeable insulation in the attic. And of course, ice dams occur when heat escapes, usually at the wall juncture. Air leaks here are especially troublesome. That can create warm temperatures on the ceiling underneath the wall, and that heat will penetrate, melt the snow, and then the snow will run down and then freeze out over the eaves, creating ice dams. There's actually circumstances when even this requirement will not eliminate ice dams. I was talking with a builder in Whitefish recently who was doing some work in Canada, and the situation came up where they had so much snow that snow is actually a pretty good insulator, that the snow was acting as such a good insulator that even following the code requirement, they were still experiencing condensation on the underside. So if there's not enough room in a joist space for the prescribed R value in a roof condition, then Montana allows R30 for up to 250 square feet or 10% of the ceiling area. So if you've got a unique situation where there's a small area that you can't get the required R38 or R49, depending on whether it's continuous, then you can have this exception, which is different than the IECC, which allowed twice the area in terms of this exception. The code requires that all access hatches be weather stripped. And if you'll notice, it says weather stripped and not sealed with caulking. For one, you can get in and out if there's weather stripping, whereas it's caulking, you have to cut the caulk, and then usually it's not sealed back up when you close the hatch down. So when you see caulking, sealing access hatch, then you know that it doesn't comply with the code. There was a change in how vertical access doors must meet thermal requirements. Previous codes, current code, the access door had to meet the exterior wall requirement. But in the 2018, the vertical access doors only have to meet the fenestration requirement in terms of R value or U factor. So there's a set of requirements in the IRC for unvented attics and cathedral ceilings. And I'm not going to go through this in great detail. I'm going to summarize it. But once again, I include this because it's having to do with insulation, and obviously that has to do with energy. But in fact, these provisions are in the IRC and not the IECC. So for one thing, the requirement, if you're going to have insulation right under the sheathing, is that you have to have a 1/4 inch vented space if you're going to have wood shingles or shakes. If you're going to use air impermeable insulation, and that would be most likely a high density foam that you spray up against the sheathing, it has to be in direct contact to the sheathing. It must have at least a class 2 vapor retarder on the surface, and you may not have a class 1 vapor retarder, meaning polyethylene, on the ceiling itself. So that's one way you can do an unvented attic. You can do an unvented attic using air impermeable insulation only without an attic at all, and it's very similar. You just have to know that you cannot have a class 1 vapor retarder on the underside of the air impermeable insulation. Another example might be as if you used rigid insulation above and air impermeable insulation below. The air impermeable insulation has to be in direct contact to the sheathing. It must have at least a class 2 vapor retarder on the surface. I'll explain those in a minute. And then once again, it may not have a class 1 vapor retarder. If you had a class 1 vapor retarder on the ceiling, it would prevent this space ever from drying out through the ceiling. If you've got a class 2 vapor retarder in the ceiling or class 3, then you would allow under certain conditions for that space to dry. So this prohibition against vapor retarder at the ceiling is to eliminate the situation where you had nowhere for that building cavity to dry. Finally, you could have air impermeable insulation directly under the the roof sheathing, and then you have air impermeable insulation over that. In that case, it actually gives you an R value for what the minimum insulation of the air impermeable insulation must be, and then the same requirements, class 2 vapor retarder on the insulation, and you cannot have a class 1 vapor retarder at the ceiling. So the history of the R value table, this is the prescriptive thermal envelopes table, just to put it in perspective. In 2009, Montana actually amended the requirement to slightly more insulation in the wall from R20 to R21, and slightly more for wall crawl space wall insulation. In 2012, once the IECC started requiring continuous exterior insulation, Montana maintained its R21 or R13 plus. This is a R13 air permeable between framing, and then R5 continuous. And then in 2015, we really didn't consider it. The IECC has stayed constant for wall frame requirements since the 2012 with their R5 continuous over R20 frame discontinuous. In Montana, I believe, I don't expect this to change, but of all the comments at the 3 public hearings held regarding the adoption of the 2018 IECC, the one I heard the most often was that we should have continuous insulation on the building envelope, and we should have tighter buildings. We'll see, but I really don't expect this to change. There's a couple of things in the 2018 that I think would result in massive builder revolt, which is not something we want, and this would be one of them. So I expect the wall requirement to stay the same, even with the 2018. So continuous insulation is defined because we now have it as a requirement. I'm not going to go through the detail of it because continuous insulation isn't required, but it does point out, I will point out that it says no thermal bridges. And so what's a thermal bridge? So you understand that term. A thermal bridge is an element that allows the direct conduction of energy and loss of heat. And a thermal bridge would be, in this case, the framing member itself would be a continuous, would be a thermal break. So if you were requiring continuous insulation, you couldn't just put rigid insulation between the studs and have that be sufficient. There's many different insulation materials. You often need information from the manufacturer to know exactly what their R values are going to be. The other thing I would mention with insulation materials is some foam tends to be air impermeable, the high density foams. There are other foams, the low density foams, that are essentially air permeable. And how you construct the, and whether or not those materials themselves count as air barriers depends on their air permeability characteristics. Rim joists have to be insulated, and you have to have an air barrier, and the best applications usually include foam. The applications of non-foam solutions usually include a lot more manual labor. Why high density foam? It's because high density foam can actually act as both the air barrier and the insulation, provide the insulation R value required. The code is now explicit about all this insulation material having to meet manufacturer's instructions for installation. And what that means, although it's reiterated now in the air tightness air barrier installation table, it means you can't compress insulation. It means that the insulation must fully fill the space. It means that you have to cut and properly fill. So this is a requirement of the current code, but it's more explicit in the 2018. So let's talk about vapor retarders. Vapor retarders are a requirement that's included in the IRC, and it defines 3 classes of vapor retarders. Class 1 is essentially impermeable. An example is polyethylene. Class 2 is semi-impermeable, and I won't bore you with the different perm ratings. It's included in the chart. And an example would be craft face fiberglass bats, which still, while minimizing the diffusion of water vapor through it somewhat, still isn't as good at stopping water vapor as polyethylene. And then you have a class 3 vapor retarder, and just sheetrock with latex paint would be an example of something that would have over 1 perm. Class 2 sheetrock, if painted with the appropriate primer or finish coat, can meet the perm rating of a class 2 vapor retarder. So the Montana, the requirement that is applicable in Montana, where you must have a class 2 or 3 vapor retarder on exterior walls, can be met with sheetrock with the appropriate paint, or it can be met with fiberglass bats that are paper faced. The requirement for vapor retarders also allows you to use class 3 vapor retarder, which means essentially it doesn't stop the movement of water vapor as long as you have enough insulation on the outside of the wall. And why would that make sense? It's because adding insulation to the outside of the wall raises the temperature of the inside face of the exterior sheathing and minimizes the chance for condensation. Why did these insulation values, why were they chosen? It's because the temperature of that surface, which we care about in terms of condensation, is a relationship of the amount of insulation on the inside and the outside. So scientists have calculated that in their view, in our climate zone, minimize the chance of condensation on the inside surface, you should have R11.25 for R21 and R7.5 for R13. Just to push it just probably a step too far, the fact that the temperature here at this surface on the inside face of the exterior surface is based on the relationship of exterior to interior insulation is the reason why putting exterior insulation on a double wall with a very high R value doesn't make any sense, because what you're doing then is creating a temperature here that will tend to encourage or allow condensation. Now, one would ask, I would think, well, if moisture condensation on the exterior surface, on the exterior sheathing is a problem, why don't we just prevent moisture from getting into that cavity? And that's what the code now does. But because we're practical, we say we still want to eliminate the chance of condensation. We don't want to put all our eggs in the basket of the air barrier. I'd also point out that building behavior is really interesting if you're a nerd, but it's also relative to a number of different factors. It's not just we sometimes think of walls as pretty static, but in fact, outdoor air temperature, indoor air temperature, and indoor relative humidity all play a role as to whether you're going to have problems with condensation in any given wall. The mass wall requirement I'm going to stop there. It's noon, and I said we were going to have a 15-minute break at noon. So we'll see you at 12:15, and we'll move along. If anybody wants to hang around and ask a question, or have anything you'd like to discuss, you're more than welcome. But you're free to go, and we'll see. I'll start back up at 12:15.
Dale, if you could unshare your screen, and I'll put the email addresses back up for the continue.
Let's see, right now they're looking at you, I think. Actually, Marianne says that they're seeing both of us. I'm not hearing him.
I forgot to unmute. So you can go ahead and share your screen. I've shut my screen down.
Okay, I'm not sure how to do that. Okay. Okay, so I think we're back in the saddle, so to speak. Carl, you mentioned a couple questions, so.
Yeah, well, I'll go ahead and
Yes.
read the one you have. Is the R value for stick frame cathedral ceiling still R38 with the 2018 code?
Well, it's going to be the same as we have the current code. The way I'd explain it is it's R38. If it's continuous, it has R38 value all the way over to the exterior wall. And R49 if it does not. So regardless of whether it's a cathedral or attic, the insulation requirements allowables are the same, with the exception of that one 250 square feet where you can have a lower R value. But the R value requirements have not changed. Was there a second question, Carl?
No.
Okay, so I'm going to go ahead and start and move ahead. We talked about the ICC 400 exception that is allowable for log construction. Previously, log construction was covered under a mass wall provision, and still could be if the individual submitting the log home construction drawings does not want to use the ICC 400 thermal requirements. So mass walls are based on the heat capacity, and previously it listed these types of above grade walls that you could apply the mass wall requirement to. It now has a heat capacity value that you could use to determine whether a wall falls under the mass wall requirements. Okay, so the mass wall provision takes into account the effect of having the thermal mass that affects the inside temperature or not, because a high thermal mass building, of course, by its very nature, stores heat longer, and so in terms of mass wall requirements by code, it's important as to whether the majority of the insulation is on the inside or outside of the wall. So if half or less of the insulation is on the interior, then you are allowed R15. In other words, if you allow the inside space to thermally communicate with the wall by insulating the outside more, you can have R15. But if you isolate the thermal wall, the mass wall from the interior somewhat by insulating on the interior, then you have to have R20. So it depends on where you put the insulation as to whether the requirement is R15 or R20. Floors are R30, and that's of course only if they separate a conditioned and unconditioned space. Basement walls, if the insulation is continuous, it's R15. If it's broken with members, framing members, then it's R19. And then there are requirements for on-grade slabs. And while I've listed a couple of IRC requirements. The ones we care about in terms of energy are protecting the exposed insulation if the insulation is installed on the exterior of the wall, and that you have to have R10 for combined 4 feet vertically and horizontally. So that's the requirement for slab on grade, 4 feet either of R10, either horizontally or vertically. And you can do it different ways. If you're going to make it install horizontal insulation, it has to be continuous with the vertical, and it has to be at least 10 inches below grade. But again, the combination of vertical and horizontal is to be 4 feet. On the interior, if you want to place the insulation under the slab on the interior, you're allowed, if you'd like to have a 45-degree angle so that you don't have the insulation exposed at the floor near the wall. But again, the requirement is R10 for 4 feet vertical and horizontal. If you've only got a 3-foot stem wall, then putting rigid insulation for 3 feet along that stem wall doesn't meet the code. To meet the code, if this were 3 feet, you would have to have some horizontal along with that vertical. By placing insulation under the slab on the inside, you not only eliminate the need to protect the insulation of grade, but you don't have the problem of how to insulate adequately along the wall if the stem wall isn't the required 4 feet. And then if you're going to have I've seen in the field confusion over how you deal with instances where you have concrete patios abutting the stem wall of the wall, and there's obviously some IRC requirements about the distance between the level of the floor and the concrete patio itself, and the slope of that patio that designers need to be aware of. But the key element is that as far as the energy code is concerned, your interior 4 feet of horizontal and vertical will suffice. If you try to insulate that on the outside of the wall, it becomes just practically much more difficult. Here's just an image of that bevel at the interior of the vertical insulation. Frost protected shallow foundations are a little complex. The information about frost protected shallow foundations is included in the IRC instead of the IECC. And what you have to keep in mind is that the building has to be maintained at 64 degrees minimum temperature, and the insulation materials used below grade must meet this ASTM standard. And so I'm going to show you some diagrams, and we're going to talk in general about frost protected shallow foundations. So if you ever have to deal with one, it'll be a little more familiar once you get into the IRC requirements. But the key element is that you've got a little bit of vertical, then you have horizontal, and you don't have a deep foundation. The foundation itself doesn't go down to frost line. And the reason this works is that the heat from the slab and foundation heats the ground below the insulation and keeps the ground below the footing, thickened footing, from freezing. If the ground below the foundation doesn't freeze, then you don't have the frost heave. But the key thing is, if you don't have heat in the building, then it doesn't maintain the thaw of the ground below the foundation. So you can't, for example, have someone want to put a frost-protected shallow foundation on a space that's going to be periodically unoccupied and unheated. So, but if you want to do a frost-protected shallow foundation, and there are some good reasons to do one, especially some additions It can save some money and time, and they can work just fine, but they are a little complicated in terms of applying. And the IRC classifies the different counties in the state according to a Montana air freezing index. And there are a group of counties over here with higher, with 4,000 air freezing index over 4,000 that are treated differently than all these other counties. So if you're in one of these 7 counties, you have to pay more attention to how you do it. But if you're in one of the non-7 that have less than 4,000 air freezing index value, then what you need to know is the minimum footing depth is 16 inches, and you have an R value for the vertical and horizontal insulation of 10, and you need vertical and horizontal length of that insulation of 48. So if we go back to our diagram, it says for most counties in Montana, you have to have a 16 inches depth on the footing, and you have to have 4 feet vertically, summed vertical and horizontal of the insulation itself. So that's basically what's required. Now, I've simplified it for these, the vast majority of the counties in Montana. If you're in one of those 7 special counties, then you have to pay a little more attention because the requirements become more specific. It has to do with the amount of insulation near the corners and the length of the insulation away from the corners. And those values are included in this table down here, but I'm not going to go through examples to show how you use them. But once you get into a frost-protected shallow foundation, you turn to the IRC, which has the requirements for those applications. The IRC also describes how you treat unvented crawl spaces, and you can do it 2 ways. You can have an unvented crawl space that has continuous exhaust from the exterior, where you have an air pathway from the living space to the crawl space, and you have a continuously operating fan that meets the capacity requirement of 1 CFM per 50 square feet of crawl space area. The other way you can design an unvented crawl space is by creating what some people have called a mini basement. You have an air pathway from the living space to the crawl space, and you supply the 1 CFM per 50 square foot of crawl space area into the crawl space. So those are the 2 ways you can have an unvented crawl space, which is by far the most common crawl space you see in Montana. Either the continuous exhaust vent in the foundation, or you supply air to the basement, or excuse me, the crawl space, and you have your pathway, which allows circulating air between the crawl space and the living space. There's yet one more option as an alternative to the exhaust fan, which is dehumidification, but I think it will be rarely, if ever, used in Montana. It's worth keeping in mind that this exhaust air here can be used as exhaust air when we start talking about whole house ventilation systems, because in fact this is a certain amount of calculated amount of house air that's being exhausted continually. There's no reason that can't be counted towards the whole house mechanical ventilation requirement that we'll talk about later. Crawl space walls can either be R15 continuous, or if you've got framing that breaks up the continuous insulation, it has to be R19. So I mentioned the fact that with exhausting air from the crawl space, it might accommodate some of the mechanical ventilation requirements, but it also could be a factor if you're evaluating whether backdrafting could occur in any given space. And that's because if you're exhausting air from any space, it creates negative pressures in that space. And of course, we have mechanical requirements for combustion air, but it's still worth being aware of how negative pressures are created in a given area if in fact there are atmospherically vented combustion appliances. The IRC requires class 1 vapor retarders on crawl space floors. There's requirements for isolated sunrooms that provide relief in terms of the R value requirements and U value requirements for the exterior walls of the sunroom, the fenestration of the sunroom relative to the rest of the building. Questions? Okay. I need to shift to a different screen, and I'm not exactly sure how to do that. The help is putting on his mask. He'll be here in a minute. I need to get back to the home screen so I can open, or to the main PowerPoint, so I can go to a different, yeah. Okay. I am informed that I have one of the slowest computers that yet remains on this planet. All right. Okay. So I know you wanted to know more about my family. If you haven't noticed, there's a theme here. This is my my grandfather on my dad's side. The Cowboys from Texas were on my mother's side. Won't bother with how they got together, but the Cowboys on the Texas side migrated to California during the Depression, as did my grandfather migrate from Missouri to Southern California during the Depression. And he went as a young man from working an orange orchard in Escondido, which is above San Diego County, in northern southern San Diego County. He would work as a baker all day, and then he'd come home and he'd maintain the orange orchard. He wound up working for Convair, building airplanes in the during World War II, continued that into the 50s, and then moved to Vandenberg Air Force Base up in Central California for the rest of his career. And he was one of the top technicians on intercontinental ballistic missiles. And so he went from orange ranching to working on missiles. Kind of proud of that. This is my dad. I love this picture because it shows the incongruity that is California. If you think California doesn't make sense, you're absolutely right. But this is my dad being a cowboy with palm trees in the background. That's California. A place for everything, everything in its place. Paul hasn't come back yet. Shame on him. So I will not call on him to tell me whether that's a legitimate quote. Yeah, it is. This is actually a Ben Franklin quote. And the reason I chose to put it here was that we're going to talk about air barriers. And location is everything with air barriers. We've talked about vapor retarders. Vapor retarders are to prevent movement of water vapor into the wall because of diffusion, through diffusion. And with an air barrier, it's preventing the movement of air and water vapor into the wall via air transport. Montana amended the definition of an air barrier, and I'm not sure if this definition will be amended. I think I proposed a slightly different version that I think is a little clearer in terms of its intent. Whether that's going to be accepted, I have no idea. But the Montana addition essentially was made to say that the air barrier needs to be on the inside of the insulation. So in the air barrier that definition that IECC has does not specify, but years and years and years ago, DEQ suggested, and it was amended so that I can currently say that the air barrier in a building in Montana is required to be on the interior. So the IECC requires that the building envelope be tested, and it requires that a set of requirements in the air barrier and insulation installation table be met. In the 2009, you had to do either, but in the 2018, as is in the current code, you have to do both. There's another provision in the code that says we're required by code official testing shall be conducted by an approved third party. Montana amended that to where it took the word third party out. It's still confusing, and some jurisdictions still require a third party somehow, even though clearly that wasn't the intent. I've recommended, and I think others have recommended, that this statement be left as written in the IECC without the removal of the word third. We'll see what happens in the past. Basically, local code officials in Montana feel they have the right to decide who can do blower door tests, and those requirements vary. Missoula is very tough, requiring significantly greater qualification. Most jurisdictions accept a one-day training that's NCAT has conducted in the past as adequate for people conducting these tests. We'll see what happens in the future. So to talk about building tightness, you have to understand a few terms. The air change rate is how we measure tightness in a building. And air change has to do with how often a volume of air is exchanged from inside to outside. In other words, if the volume of air inside a building exchanges fully with outside air within an hour, you could say that air change rate is 1. And we often write that as 1 ACH 50. Obviously, that's air changes per hour. The 50 stands for at the test pressure of 50 pascals, which is just a pressure that's been chosen for these test purposes. So the current code of Montana says buildings can be have to be at least 4 ACH 50 in terms of tightness, meaning that the total volume of air in a building cannot exchange more than 4 times in an hour. So that's ACH 50. The history of the building tightness in Montana, 2009, Montana made it buildings tighter than the IEC called for. Then since then, Montana has maintained its requirement of 4 ACH 50, while the IECC has required 3 ACH 50. The code update hearings, the listening sessions, the most commented on requirement was having to do with building tightness, saying Montana should go ahead and require 3 ACH 50. I doubt if it's going to happen. My money's on 4 ACH 50 being the required building tightness in the future. The big thing that happened from the current code to the 2018 in terms of this table, the table addresses both air barriers and insulation, but in the past they weren't separate columns for the 2 different materials because they didn't work out as well when they tried to have a single column for both air barriers and insulation. By isolating them, they've made the language somewhat, not fully, more comprehensible. So it's a different form, and the requirements for air barrier, they have to be continuous, they have to be sealed. You can do that either with polyethylene and continuous in the wall with sealants at the sealing at the joints. You can't just lap polyethylene and call it good. The code requires that it has to be sealed, and it has to be sealed top and bottom. You can also use a sheetrock. Gypsum board is just fine as a class 2 vapor retarder and as a air barrier, as long as you seal it at the top and bottom plates and whenever there's a penetration. So you can use either the drywall based or you can use the polyethylene based approaches to creating an air barrier. It both satisfy code. The drop ceilings, you're to align the insulation with the air barrier. You're to seal at penetrations in the ceiling. You're to seal at top plates, at the junctions of where walls meet the floors and the foundations, and you're to seal at the knee walls, which are always a real challenge to have a continuous sealed air barrier. The air barrier requirement includes sealing with non-air permeable materials around window and door frames. You have to have an air barrier at rim joists, meaning you can't just stuff bad insulation or paper-faced insulation and call it good. You have to have an air barrier at other areas where the end of floor insulation might be exposed, such as at a knee wall attic condition. You have to have a class 1 vapor retarder on the floor of a crawl space. You have to have penetrations by mechanical and electrical elements in the ceiling sealed. In the case of anything around a flue, it has to be obviously fire rated as appropriate. You cannot use air permeable insulation for that material, for that ceiling. And there's a particular requirement that at garages, you have to seal at penetrations and at joints. And of course, garages being connected to houses, make absolutely no sense. Garages produce carbon monoxide. They often contain paints and vapors. That we have garages connect to houses, personal opinion, makes not a lot of sense. But at least in the air barrier table, they have some requirements that you have to seal it so that you minimize the movement of those everything from carbon monoxide to vapors from paints so that will not move into the house. Recessed light fixtures must be sealed to the finish material, and you have to have an air barrier behind the tub and bathtub. You can't use the tub enclosure or shower enclosure itself as part of the air barrier. You have to seal the boxes for electrical boxes, or you provide some sort of pre-made airtight box that is provided that have seals inherently for the wire attachments. That you have to seal all those electrical boxes. And when there's unconditioned space below a floor, you have to seal the boot of the HVAC. Montana doesn't require sprinklers for houses. If we did, if you have concealed sprinklers in a house, in a residence, then there's some limitations that basically say, don't prevent the the sprinkler head from operating by filling it with foam or something like that. Then the insulation requirements is that you can't use air permeable insulation as a ceiling material. Once again, it reiterates that you have to align the insulation with the air barrier, and let's look at why. If you have an air barrier that's in blue here in this diagram, then you can have air and heat move from the attic down into the soffit, and you have then very cold temperatures in the soffit, and those temperatures aren't, you've not insulated that space from the interior, so you can have significant heat loss, whereas if you were to locate the air barrier up here adjacent to the insulation, then the air would not be able to move down into that soffit, and you're not going to create what's often called a thermal bypass by mislocating the air barrier. See, that's a common thread, is you align the air barrier with the insulation. You have to insulate at headers and at corners. Rim joists must be insulated, and you are to maintain contact insulation to floor joists, floor sheathing when you're insulating a floor, usually above a garage. So you can't have this gap between the floor and the insulation itself. You're to have the insulation in contact with the floor sheathing, underside of the floor sheathing. Crawl space insulation must be attached permanently to the walls. You are to cut and fit small spaces with bad insulation. In other words, you're not to just stuff it in there. And then the recessed fixtures have to be airtight and IC rated. IC means it's you can put insulation. The fixture has been designed to accept insulation over the top. Keep in mind that even though they call them airtight, they're not very airtight. And if you're interested in a high-performing home, you're not going to put recessed lighting boxes up into the ceiling where there's insulation. With LED slim mount lamps nowadays, there's almost no reason for this anyway. And then insulation, you have to carefully fit insulation around penetrations, whether it be plumbing or electrical, and not just depress the insulation. Exterior walls must be insulated. That makes sense. And for fireplaces, this is not new. You have to have tight-fitting flue dampers and doors and outdoor combustion air into the firebox. So the IECC requires that the building envelopes be tested. It's mandated in the 2012, and of course that's been maintained since. So the 2012 provides almost no information, or at least very little information about how to conduct an envelope air leakage test. The IECC 2015 version added a couple of standards that provided more detail on how you're to do a blower door test. And then the 2018 IECC added yet another standard, the ICC Resonant Standard 380, that not only details how you're to do a blower door test, but it details how you to do a duct tightness test. So building testing, if you're not familiar with it, is using a big fan. We call it a blower door with a big fan inserted into a fabric sheet in an aluminum framework, so that you create basically a big exhaust fan for the house. You exhaust the fan until you achieve a certain pressure differential between inside and outside the house. That's 50 pascals. And when you've achieved that test pressure, the amount of air that blows out of the fan is equal to the amount of air that enters through leaks in the building envelope. And we know that because that's physics. And so this is how we estimate the building tightness. You have digital manometers that make it much more easy to do the test. You just need to be able to set the test up and set the manometer up properly to get an appropriate result. And you get a flow in CFM, cubic foot per minute, at the test pressure. And we'll come back to blower door tests, but I wanted to talk about a provision in the 2018 IECC that I don't think there's much of a chance it'll reach Montana, but the IECC 2018 requires combustion closets for any atmospherically vented appliance. The idea being that what we often do now is set a gas water heater in a basement, and then because we don't want it to backdraft, we put a 6 to 8 inch diameter hole in the wall for combustion air. And somebody said, well, that doesn't make any sense from an energy point of view. And they said, well, if you really want to have atmospherically combusted appliances, most of the time today, that's just the gas water heater, because high efficiency sealed combustion furnaces are so common. Then you'd have to put that atmospherically vented water heater in a closet, insulate the outside of the closet as if it were an exterior wall, and provide then fresh air for the combustion air in for that appliance, but you've thermally isolated it from the rest of the building. It's a great idea, but it's probably not going to see the light of day because it will add several $100s to the cost of a building, and be one of those red flag items for builders. Recessed lighting fixtures, there's an actual CFM leakage rate at a particular pressure for what those recessed light fixtures are. Recessed into an uninsulated floor cavity, not a problem. It's just insulated, meaning recessed into insulation, where you have to deal with the tightness. So this is somewhat humorous, but I was basically asking, what are all the things that can make it difficult to maintain the integrity of a wall, prevent moisture damage? And so here are all the my list of things that can happen despite a designer and sometimes a builder's best effort. Sheetrockers come in and slice the polyethylene because it's easier to put the sheetrock up in the corners. Plumbers use Sawzall as if they were an artist's brush. If they're not careful, they really don't care what they're doing with it, as long as it doesn't have to do with plumbing. Electricians sometimes go crazy with their boring bits. People put hot tubs in houses, and it makes no sense because there's no way to deal with the humidity from a hot tub. It's just asking for problems. You can't. We couldn't afford to build houses to have the ventilation necessarily to deal with the humidity you get from a hot tub. Noisy exhaust fans are a problem because people don't use fans if they're noisy. So low zone fans, fans that are not noisy, means you'll probably have ventilation being used over time. If they're noisy, they won't be used. My wife's indoor plants is an issue in our house. I don't know how big of an issue it is nationally, but anything that puts excessive moisture into the air is a problem. We don't have any other sources of moisture in our house, so that's probably a minor problem. So those are all potential issues with maintaining integrity of the wall and making sure warm, moist air can't get into a wall, therefore the air barrier. Any questions? Beer is proof that God loves us and wants us to be happy. Did I have this one up before? I did. Well, he didn't say that. What he said was, did I have this up before? I can't remember. Anyway, let's skip on. It sounds as if Ben Franklin liked both beer and wine, is my conclusion from the quotes. Programmable requirements are required. Programmable thermostats are required. Supplemental heat must be controlled in a heat pump. When the compressor can meet the load, the supplemental heat shouldn't turn on. And in the past with heat pumps, that's been one of the big issues, is not only their performance in cold climates is really improved the last few years, and so have the controls. But this is just trying to make sure that the supplemental heat isn't operating when it doesn't need to, and you get the benefit of the operation of the air-to-air heat pump. There's an outdoor setback control required for boilers so that you lower the boiler temperature when the outdoor air temperature is higher. The duct insulation requirements have changed now in the 2018 version. The insulation required around ducts is based on its location and the size of the duct. And so there's nothing here that's going to be alarming in terms of radically different values. It's just that in some locations for lower volume ducts, they're allowing a little bit less insulation. Ducts and air handlers are to be sealed. The sealing of the air handlers is accomplished at the factory, but ducts are to be sealed. And what you see often is that they paint this duct mastic, and the code does actually require certain types of materials that meet certain requirements. What I see is folks skimping on the duct mastic and it being more like a painting on a layer of paint instead of actually something that's going to last for years. It should be about as thick as a nickel, always should have been. And if you follow the manufacturer's instructions, which is a requirement for all products used on a job site, then it would be essentially as thick as a nickel. The code also requires that you test the ducts for tightness. And starting in 2012, the IECC allowed only a total leakage test. Previous codes had allowed a leakage to the outside test, and Montana made an amendment requested by the builders to allow a leakage to the outside test in addition to the total leakage test. And the big issue with that is that both of the types of tests had the same metric. It's 4 CFM allowed for every 100 square feet of conditioned space. That's why we cared earlier about the definition of conditioned space. In the 2018, I'm hoping that Montana does away with this amendment. I don't think anybody asked that it continue into the future, and that in the future, all we'll have is a single test to do, a total leakage test, and the tightness of the total leakage test has not changed from the current code. The difference will be is the total leakage test will be the only one required. It will only be required if any of the ducts or air handler are outside the conditioned space. So you don't have to test duct tightness unless the air handler or the ducts are outside the conditioned space in the 2018 IECC. The 2021 will require all ducts be tested regardless of location, but the 2018 will allow only the total leakage test and still allow for the ducts, if everything's inside, air handler and the ducts, to not be tested. If you're unfamiliar with duct testing, I'll explain it really quickly. So with duct testing, you're using equipment very similar to the equipment used for blower door testing or envelope testing. You have a small fan that you hook up to the duct system. You seal all the openings to the duct system, and you pressurize the duct system to a test pressure of 25 pascals, and you see how much air you have to blow into the duct system in order to achieve the 25 pascals. And that volume of air is the duct leakage. Air in equals air out. And so that's how you conduct a total duct tightness testing. The biggest problem and challenge is to find and seal all the openings of the duct system. But the industry is used to doing these kinds of tests now, so it shouldn't create much of a hardship. There is a way to do duct leakage to the outside testing. It's necessary if you were to do an energy rating index certification through the ERI path, but otherwise that's the only reason total duct leakage to the outside test would be used. In this test, you're able to isolate the leakage that occurs when the ducts are located outside the thermal envelope. You do that by using a blower door to bring the house to a 25 pascals of pressure relative to outside. Then you use the duct tester fan to bring the sealed duct system also to 25 pascals relative to outside. And the amount of air necessary to bring it up to that equal pressure, so there's equal pressure both in the duct system and the house, will tell you what the leakage is to the outside. And it's a little more complex, a little bit more prone to error, and that's why I'm glad, or will hope, that the leakage to the outside is not an option for testing duct leakage according to the 2018 IECC. And the 2018 does require, is explicit in requiring a written report about the results of the duct tightness test. And it's explicit that the heat recovery ventilator, and energy recovery ventilator, these are ventilation devices, are the ducts associated with those, unless they're integral with the ducts attached to the air handler, do not have to be tested. So use of building returns, building cavities for returns has always been somewhat of an enigma or a controversy. In the 2012 through 2018 IECC, the use of cavities for returns on ducts is prohibited. Montana amended that, and you can still use the building cavities as return ducts. I don't know how that amendment will move forward. I realize that builders don't want to go to the cost of providing, hard ducting on the returns. My concern is indoor air quality and indoor safety, because if you have leaks in the returns, you can more easily backdraft atmospherically vented appliances. So I recommended that they allow cavities returns only if there are no atmospherically vented combustion appliances in the building. I have no idea what the state will do. There's in the past, you could bury ducts in the insulation in the attic, but the code didn't tell you exactly what you needed to do it. So the IEC 2018 added provisions that say that you are to have your R8 duct insulation and a total of R19 insulation above and below. If you have that, then you meet the code requirements for having a air duct in the attic. Then, because of the addition of the Energy Rater Index compliance option, they came up with a definition of when you could consider ducts located within conditioned space if they were in the attic. This is important because of the software that does that analysis treats ducts that are located in the interior of the thermal envelope different than in an attic. But if you have a combination of both duct insulation and attic insulation, that adds up to the total requirement, R14, R49, or R38 if it's continuous over the exterior walls, then you've met the requirement for ducts located in conditioned spaces. Again, this is only this provision is only applicable if you're doing an ERI type analysis. HVAC piping with fluids over 105 degrees have to have R3 insulation. Hot water pipes have to have R3. There's currently an amendment to the 2012 that eliminated some requirements for more additional hot water piping insulation. In the 2015, the IECC did away with the elements that were amended. So basically, the national code caught up with Montana. Essentially now, hot water pipes have to be insulated to at least R3. And then if you're going to put on heat recovery devices from drain water, there's a Canadian standard you have to meet. So build it right, ventilate it tight is a mantra that building scientists have been using for years. And it's saying that the way we build buildings now we have to break for 5 minutes because it's 1:05. So this is going to be our last break until we end. And so I'm going to give you your 5 minutes now, come back, and then we're going to go till we end. And I promise it won't be beyond 2:15, and hopefully I can hit it closer to 2. So you're free for 5 minutes. I'll start up at 1:10. Okay, so I'm going to start off this section, and we're talking about mechanical ventilation, and the mechanical ventilation requirement was added to the IECC, and a provision that addresses it also was added to the IRC in the 2015. So, Carl, can you hear me? Okay, I'm talking to a couple of screens here, and I just didn't know if there was life out beyond our planet. So the mechanical ventilation requirement, the whole house includes the mechanical ventilation requirement that was added in the 2012 and maintained in the 2018, has 2 parts, and it's easy to get it confused. But part 1 is whole house ventilation, and part 2 is local ventilation. You have to adhere to both of the requirements for both of those in order to be code compliant. So the whole house mechanical ventilation requirement is based on a table, and this table, you use the floor area, conditioned floor area of the building, and the number of bedrooms to determine the airflow required for whole house mechanical ventilation. The assumption with this table is it is continuous. And so, for example, if you had a 2,000 square foot 3-bedroom house, you would have to provide 60 CFM of continuous airflow in that house in order to meet code. The ventilation requirements of that table haven't changed between the 2012 and the 2018 IECC, but the 2018 IECC added a formula to calculate the requirement more precisely. And the formula is 0.01 times the total conditioned house floor area plus 7.5 times the number of bedrooms plus 1. This value, number of bedrooms plus 1, assumes you have 2 people occupying one of the bedrooms, gives you an estimate of CFM. It's how the table was derived. Oftentimes you can shave a few CFM off of the required CFM by doing the calculation as opposed to using the table. So not only do you have to provide the whole house mechanical ventilation, you have to provide a occupied accessible on-off switch, manual switch for that ventilation system, even if it's continuous. And if you choose, rather than having continuous ventilation, to have intermittent ventilation, there are a set of requirements you have to follow. It says that you have to take the requirement of the table and use a factor based on the percentage of the time that it's operating. If the ventilation system you're installing is meant to operate 50% of the time, and it must operate 50% of each 4-hour segment, not just 50% of the entire day, it has to operate 50% of each 4-hour segment, then you would have to oversize the fan by 2. And there are these other factors based on the percentage of the 4-hour segment that's going to be operating. And the factor obviously says that if the fan isn't going to be on all the time, then you have to increase its capacity. There's also a requirement for the fans associated with whole house mechanical ventilation. This table does not apply to the local exhaust fan requirement, but for the whole house mechanical ventilation requirement, it has an efficacy in terms of CFM per watt for those fans involved. And in 2018, they added a heat recovery ventilator, an HRV, and an energy recovery ventilator, an ERV, to this table. And so whether you're using range hoods, inline fans, bathroom exhaust fans, it gives you what the efficacy needs to be. And I would point out that it lists range hoods here. They're talking about a range hood with exhaust to the outside. They're not talking in this table about a recirculation range hood. So now let's talk about local exhaust. So in addition to the whole house mechanical ventilation, you need to deal with local exhaust in the kitchens and bathrooms, and you can do that either by continuous or by intermittent. And the table includes the values. For kitchens, you're either 100 CFM intermittent. That could be an on-off switch. It could be a timer. It could be a dehumidistat. It's just not continuous. And if you're going to have it operate continuously, then you only need 25 CFM continuous. The values are 50 and 20 respectively for toilet rooms. So let's see how you'd apply that. You've got a house that's 2,000 square feet. If you go back to the table, it would tell you that a 3-bedroom house of 2,000 square feet would require 60 CFM continuous exhaust. So you could install a 60 CFM continuous exhaust fan that meets the efficacy requirements of the table we just looked at in the bathroom, operating continuously. Then you could install an intermittent exhaust fan at the kitchen. It could be in the ceiling. It could be a range hood with exhaust to the outside, as long as it met the 100 CFM intermittent requirement. This then meets the mechanical ventilation requirements. You've met the whole house mechanical ventilation requirement. You've met the local exhaust requirement. Another example is a larger house with 4 bedrooms. If you look and see what the requirement is for continuous ventilation, it's 90, I'll tell you that. And so one way of meeting this requirement would be to place 45 CFM continuous exhaust fans in each of the bathrooms. That gives you the total 90 CFM continuous exhaust, which complies with the whole house requirement. And then you've got the same 100 CFM that in the kitchen that meets the local exhaust requirement. Another option would be in that same house, you still need 90 CFM continuous. You could have a central exhaust fan that exhausted 20 CFM from each of the bathrooms, meeting both the local and continuous for each of the bathrooms, and then sending 50 CFM from the kitchen. So you've met the total 90 CFM that you need continuous for the whole house. And in fact, the continuous ventilation that you've provided in the bathrooms and the kitchen meet the requirement for local ventilation. So once again, you design the mechanical ventilation system such as it provides both the continuous and the local. They can be separate or they can be the same. This central ventilation system could recover the heat and use of a heat recovery ventilator and provide balanced ventilation. You'll notice that in none of these examples do we show where the air is going to come from, because we know if we're exhausting 90 CFM from the house that we're going to be drawing 90 CFM through the leaks in the building envelope. And if we were to want to balance that, we would provide, we would design in air ports or entry areas for where the air is going to come into the space. A heat recovery ventilator brings air in and exhausts air out, and that's an example of a balanced system. Balanced system is not code required. So you can have different kinds of ventilation systems. The code doesn't detail how you do it. You can have ventilation systems that are integrated with the air handler. You can have ventilation systems that are separate. Separate systems tend to be more effective. Balanced and exhaust systems, meaning you can have designed entry areas for the makeup air, makeup for the exhaust air, or you can just exhaust the air, and you have to then assume that air is going to be brought in from the outside through any leaks or penetrations in the building envelope. Heat recovery ventilation might be a good business to be in given the COVID virus, because whether it be commercial or residential, ventilation and essentially dilution of air is the one strategy that has been discussed universally as a way to deal with some of the implications of COVID. Residentially, there's only a few things that a person might do to, let's say, improve the safety of a home. Increased ventilation may be one of them. There are other things that people might consider, such as isolating bedrooms and bathrooms in case somebody in the house gets sick, and so forth. Where the real changes are going to occur are over on the commercial side, because on the commercial side, the implications of drastically more ventilation, seriously considering the practicality of spaces that use cubicles, open office spaces are going to be all of a sudden problematic. And it'll take a few years to see how that all settles out. But there will be implications, especially on the commercial side, for dealing with potential viruses. And even on the residential side, if you think about it, there might be a few changes in the way people design their homes, home offices, and isolation areas in case somebody gets sick. It'll be interesting to see how that ultimately turns out. The code requires that in residential, automatic and gravity dampers be installed at intakes and exhausts, pretty straightforward. And we're moving into the mechanical, obviously moving in and discussing the mechanical components. The code continues in 2018 to require that the heating equipment be sized and designed according to ACA Manual S and ACA Manual J, or a equivalent design procedure. And one of the things that I think needs to improve in general is the folks that are submitting plans for permit, the construction documents actually include the information about the type, size, capacity, and efficiency of the heating and cooling systems and hot water systems. This is not something I see a lot of. Certainly building departments, I hope, will begin to require this at plan submittals, and not just allow builders to wait until the building is put up and just wait and see what the HVAC contractor decides to put in the house. Obviously, someone performing a plan review will, it behooves them to require enough information that they can judge, in fact, whether these designed protocols have been used. And that's often not the case. But I certainly believe that the more complete the submittal drawings are, the contract documents submitted for a permit, the more likely we're actually going to see those energy efficiency elements in the building itself. If you've got multi-family units, meaning more than 2 residential units or dwellings put together in a building, you actually have to go use sections 403 and 404 of the commercial code instead of the residential code. It doesn't happen a lot. Most of the time, dwellings are heated and cooled and ventilated individually. But if the systems serve multiple dwelling units, you've got to go over to the much more complex commercial side of the energy code. Snow and ice melting equipment have to have shutoffs. Pools and spas has a set of requirements that make sure that there are controls to keep the pump and heater from working continuously, and a cover. Before moving on, I guess we'll stop and see if there are any questions. That was a little bit of a short section. I'm going to move right on. So Paul, did Franklin actually say whoever would overthrow the liberty of a nation must begin by subduing the freeness of speech? Absolutely right. He hasn't missed one yet today. So this is a Franklin quote. It probably has absolutely nothing to do with lighting, but the 2018 lighting requirement is now that 90% of permanently installed fixtures have high efficacy lamps. The only difference in the 2018 from the 2015 is that it now makes it slightly more difficult to have a to get included in what a high efficacy lamp is. Obviously, LEDs fall into the category of a high efficacy lamp. So 90% of all installed fixtures have to be high efficacy, and the 2018 makes high efficacy slightly more difficult to meet that standard. So we've been talking about code requirements, and we talked, especially when we were addressing thermal envelope, about the prescriptive approach. The simulated performance approach has been in the code for a long time, and it provides maximum flexibility. In other words, you can do a computer model of the building. In other words, you turn the square footage of wall area, windows, and so forth into areas. You note their energy characteristics, and you then model their energy performance. And what the performance alternative allows you to do is compare the actual energy cost between a standard reference design and a proposed building. The standard reference design is created by following a table in the code that explains exactly what you're to assume for the standard reference building. And then you do another model that is based on what the proposed characteristics are. Then you turn the energy use into energy costs, and you make that comparison. The tools that would probably be used for simulated performance are like RIM rate or RIM design, common home energy rating software, energy gauge, ecotrope, or a couple of other software names that are out there. REScheck can in fact be used for simulated performance, but it's very, very limited, as I mentioned earlier. And I don't see any benefit to trying to use REScheck in a performance analysis. So just to reemphasize, the simulated performance alternative, as in fact the energy rating index, creates a standard reference design and a proposed design, compares the two in terms of energy use and therefore costs. These geometric twins are compared, and as long as the energy cost of the proposed design is less than the standard reference design, then the building complies as long as it meets the mandatory requirements. The energy rating index was new to the 2015. It's not in the 2012. It's essentially a home energy rating option, and it adds a fourth compliance approach as an option, and the ERI compliance approach is in section 406 and provides a flexibility. Now, where did this come from? It came from the advocacy of a number of production builders on the national scene who went into the codes making process and said, we want a more flexible approach of how we meet the energy code. And therefore they added, lobbied for and got the ERI added. And the one thing that they really wanted was the ability to trade off HVAC efficiency with building envelope thermal efficiency. And you can do that in an ERI approach. You cannot do that in the simulated performance approach. And the basis for how you do it is essentially dictated by the standard approach defined by the folks who do home energy ratings. That's the Residential Energy Service Network, or RESNET. And so RESNET ANSI ICC standard 301 must be followed in order to perform a home energy rating index analysis. So it's completed, the ERI analysis to be completed by a third party, and their documentation and compliance reports must be submitted to and reviewed by a code official. The way it was envisioned that an ERI would work is that you would do that the home energy rater essentially would conduct the analysis, do the computer analysis, and then actually inspect the building to make sure it meets not only the characteristics assumed in the computer modeling, but also the other mandatory requirements of the ICC. And so I think it's a good idea if anybody who's going to actually be inspecting for code requirements, that they be certified as a residential energy code inspector by ICC. I'm not sure if the state is going to make that requirement of someone who's conducting the ERI index. It will essentially be up to a local code official to decide who's appropriate for conducting an ERI analysis. If you're not familiar with ratings, they were introduced about 20 years ago. They're essentially a computer analysis of the building's energy performance, and a home that gets a score of 100 is built to complies with the 2006 IECC. A building that has a HERS index score of 0 is producing, usually through solar, as much energy as it's using. So the ERI requirement in the 2018 IECC is 61. So if ERI becomes a compliance path in Montana, then the ERI analysis will have to achieve at least 61, and the mandatory requirements of the code will have to be met also. So that's basically the general summary of the ERI. In 2015, the IECC was 54. In the 2018, it's 61, meaning it's a little more lenient in 2018 than it was in the 2015. In the 2021, it actually goes back to a little more stringent requirement. I think the only other thing and this just reemphasizes, and you should at least be aware of the fact that the ERI score requirements differ based on climate zone, and Montana is in one climate zone. So the entire state, in terms of an ERI compliance path, would have to meet 61. There's also a requirement that says if one of the things about ERI that some designers wanted the capacity to use is to be able to count the renewables. as making the building essentially more efficient. So in order to sort of protect the integrity of building envelopes, they said if you're going to use renewables in the ERI analysis, you're going to have to at least meet the 2015 in terms of thermal envelope requirements. If you don't use renewables, then your building envelope at least has to meet, as a minimum, the requirements of the 2009 IECC. One of the things that's included in the ERI, or energy rating approach, is insulation quality, and the way they do it is by determining by dictating a maximum number of leaks, gaps, which of course lead to leaks. So it has a maximum amount of gap, and then a maximum amount of allowable area that's compressed to a certain amount. So based on the area of gaps and the area of compression, your HERS rater will be able to grade insulation as either grade 1 or grade 2, which allows a greater percentage of gaps and a greater percentage of compressions. And anything that's not grade 1 or grade 2 gets rated as grade 3, and the ERI software downgrades the performance of the wall based on these grades. That's a part of the ERI. It's not currently a part of the code. Anybody have any questions? There's a new chapter in the 2018 IECC, and the chapter is called Existing Buildings. It was actually added in the 2015. And what it does is it takes the provisions in the code that address additions, alterations, and repairs and change of occupancy, and puts them in one place, and provides a little bit more detail on how they're to be applied. So the change of occupancy is straightforward. It says that if you change a residential occupancy to a commercial occupancy, you then have to comply with the commercial code. If you change a commercial occupancy to a residential occupancy, then you have to comply with the residential existing buildings provisions. But it provides an exception that if you're doing an ERI or a simulated performance approach, you're actually allowed an additional 10% if you're going from one occupancy and changing it to a residential occupancy. So that's the change of occupancy requirements that are now included in the 2018 in the existing building section. What to keep in mind with existing buildings is that if the building is unaltered, then those portions that are unaltered do not need to comply. So it's only those portions that are new or significantly altered that that come under the requirements of the IECC. So for additions, there's actually 3 ways for compliance with additions. You can just look at the addition itself. You can look at the addition plus the rest of the building as a single building. And you can do an analysis that says the addition plus the existing energy use, the existing building energy use, has to be less than the existing if you're using a performance approach. So most of the time when you're going to do addition, you're just going to look at just the addition, but it's not the only way you can approach it. And there are these three options then. So the envelope, the HVAC, the hot water systems and lighting for additions must all comply with Chapter 4 and its battery of requirements. The building and the duct leakage, building and duct tightness still needs to be tested unless there's less than 40 feet of duct in the addition. So there's lots of questions about how that's to be done based on the unique characteristics of an addition. So there's a lot that a code official and builder designer would have to work on to talk about exactly, for example, how do you test the tightness of an addition if you've just enlarged a living room and there essentially is no wall between the existing and building and the addition. There's ways to approach it, but those ways are not necessarily explicit in the code itself. Alterations, if you're significantly altering an element of the building, it's to comply with the energy code as a whole, except there's a bunch of important exceptions. Storm windows are not, you don't have to apply the whole code to the storm windows. If you have exposed existing ceilings, if you don't expose existing ceilings or walls, and they're already filled with insulation, then you don't have to change that. Where you've got an existing roof, wall, or floor, and you're not exposing the insulation, you don't have to change that. If you just put by recover, they mean a covering over the existing roof, add another layer, then you don't have to comply with the energy code. Then there's the most confusing of the exemptions, which is to apply to a situation where you have insulation either directly above or directly below a deck. And if this is the circumstance, then it says that if you expose the sheathing, then you are in turn required to make it meet the thermal insulations for a ceiling. And then if you want to apply a surface film to an existing single pane, then obviously, or at least reasonably, you don't have to comply with the rest of the window requirements for the building. So those are the important exemptions for alterations. Alterations, again, you must test the ducts unless the addition is less than 40 feet in length. You must comply with the hot water system requirements. The lighting must comply with the lighting requirements if you're changing 50% or more of the fixtures in the space. If you're changing less than 50% of the fixtures in the space, then the space does not have to comply with the lighting requirements of the energy code. And once again, if you do a performance approach analysis of the existing building alteration, you're allowed this 110%, this 10% factor of additional energy cost associated with the alteration. Repairs are not covered by the energy code, and examples are glass-only replacements, roof repairs, or if you're exchanging just the bulbs and ballasts in a lighting system, those also are not do not fall under the requirements of the code. So, any questions? So, I'm not sure if this is going to be how the state is going to treat it, but in the 2018 IECC, there's a solar ready appendix, and I and others have recommended that the state include adoption of the solar ready appendix so that local jurisdictions will have the option of adopting it for their jurisdiction. It wouldn't be required of the state as a whole, but if a jurisdiction decided that they want these elements of the solar ready appendix to be adopted or be a requirement, then they would have that option. And by solar ready, what we're talking about is not fully installing, and quite frankly, we're almost always talking about solar electric system here. Seldom are we talking about solar water heating or other systems. But what it's saying is that if it's much more cost effective if certain elements are installed in a building when it's first constructed, rather than waiting until you're actually installing the solar system before you figure out how you're going to get the electric wiring to from the panels to the breaker, how you're going to, are you going to have enough room in the room where you've got the breaker box to install a panel or associated with the solar. So what the Solar Ready Appendix does is have a set of requirements that would say, okay, put this in when the building's built, and then if somebody decides to actually install the photovoltaic panels later on, it'll be much less expensive than adding these later. And so you have to, as an element of complying with this Solar Ready Appendix, you would have to identify a Solar Ready zone, and the appendix has some requirements in terms of 600 square feet at least, and a certain at a certain angle relative to the sun southern aspect. No obstructions. You need to make sure that the roof is, from a structural point of view, capable of handling a solar collector system. You have an interconnection pathway from the solar system to wherever in the building it needs to connect to the electrical system. And then you have to reserve electrical space in the main panel for the addition of the future photovoltaic panel. And you have to document that all this exists near the electric panel. And of course, it makes no sense to require solar ready if the building is directly north of a multi-story building or otherwise is blocked from having the sun. So it says you don't have to meet the Solar Ready Appendix if the roof is shaded for more than 70% of daylight hours. So it has the option to it explains therefore when you need to apply the solar appendix or not. I could see Missoula, Bozeman considering adopting the Solar Ready Appendix for their areas. Other areas may absolutely choose not to, but the state has to decide if the local jurisdictions are going to have that option. Any questions? So this is a couple of websites that I think would be useful if you're interested in further information about energy codes. The DOE has an energycodes.gov website. That's the website where you could find REScheck, the residential energy compliance program, and ComCheck, which is a software they have that assists in compliance with the commercial code. Both of those available at energycodes.gov, as are numbers of articles and resources having to do with residential and commercial codes. And then Montana Department of Environmental Quality, basically the energy office in Montana, has a website that where they provide specific information about energy codes, and they are the source for a summary of the energy code that's applicable at the time, and of course the labels that we looked at before. And that's that commercial as I did for you, Paul, talking to Paul Cheetah with DEQ. Now I'm going to shift off to talk just for a minute about the 2021 IECC, just so you know what's coming down the pike. And I need Jason over to assist me in shifting to a different slide deck. I'm informed that we should be back in operation. Oh, yeah, I've actually figured that out. But, okay. Okay, so let's look ahead to what's in the 2021 IECC. The okay, just reminding myself what I did. The our family of energy codes in Montana in large part adopts the family of codes produced by the International Codes Council, and they review and update those codes every 3 years, and so there's obviously a 3-year cycle. And at the point they are now, they've just decided what the final provisions of the 2021 are going to be. It's yet to be published. So what I'm going to talk about is garnered from various websites and discussions about what went on in the discussion about the 2021. And the process is a little bit controversial in the moment, and there's actually some appeals as to the decisions that have made, because the International Codes Council procedure is they have a group of people. They have some committees that look at the energy code, and then they have kind of a large conference and typically the committees would decide what should be changed after doing research, and then they'd have essentially a large conference, and there would be a vote at that conference, and people would make public statements, pro and con, various amendments. And the last couple of cycles have been a little different. And in the 2018, they allowed voting by by participants that are not actually in the conference. And so it largely local government and employees from a local government could potentially be a voting member. And so they went from a smaller group making the decision to a larger group that are making the decision. And in the 2021 process, the committees went through and made their recommendations up or down relative to the various proposals. But then the larger group that included some online voters disagreed with the committee and approved a number of measures that the committees had voted down. And so there's some machinations within the world of ICC as to whether that was appropriate, and whether if this sounds scarily familiar about the discussion of will the next national election actually mean anything, it's because the similarities are there. There are people who are arguing about the validity of the votes that have been cast by the online participants. It doesn't affect our life other than to understand that this is not a pretty process sometimes that goes on in creating what goes into the IECC. And but we do have a good idea of what most likely the 2011 IECC will look like. But I will also say this: it's very little chance that Montana will ever consider the 2021 IECC, because it's taken so blankety blank long to get to adopting the 2018 IECC. So my best guess is that the 2021 IECC will be skipped over the next time Montana considers adopting and modifying their energy code. It will be most likely with the 2024 IECC. But that given, it's interesting to see what the 2021 actually does. In its definition of its scope and administration of intent, it's added renewable energy systems and energy storage systems that were not present in the previous versions of the IECC. And the building envelope components of elements of the 2021 IECC, in my view, don't appear to affect zone 6, which is Montana. So 21 doesn't really change the building envelope requirements. Interestingly enough, HVAC, in the HVAC section, ducts are actually required to be tested regardless of whether they're inside conditioned space or not. And it requires that ventilation systems that are part of the whole house mechanical ventilation system now would have to be tested. So in the 2018, you don't have to test, for example, an heat recovery ventilator ducting system, but you would in the 2021. The efficacy of ventilation fans in the whole house ventilation system the efficacy would be increased a little bit in the 2021 from the table that was in the 2018. And this I thought was interesting. The energy recovery or heat recovery is mandated in the 2021 for zones 7 and 8. It's not mandated for Montana, but I thought it was significant that the IECC now is requiring heat recovery for at least slightly colder climates than Montana. It's kind of like writing on the wall. Lighting power, they increased the standard for efficacy, and this is significant. It requires lighting controls to dim or automatically turn off all the lights in the residence. So that's big. They're now moving the lighting controls that have been up until now only required for commercial buildings into residential buildings. And for multifamily buildings, they're saying that exterior lighting requirements are per the commercial code. Again, that hasn't been the case, won't be the case for the 2018, but it looks like that's the case for versions of the code beyond the 2018. And in a very controversial move, they're requiring electric vehicle charging stations in homes. And again, this is one of those issues that we received a lot of discussion and is not insignificant. I think energy efficiency advocates have become frustrated with how shallow the line is in terms of energy efficiency improvements. And so in the 2021, they added a set of flex packages. If you're familiar with the commercial code, what was required even in the 2012 version of the commercial energy code was a set of optional packages. Commercial designers had to choose one of 5 options that had to be added to the building design. And in a similar way, here in residential, they're saying there are 5 additional, they're calling them flex packages that must be adhered to if you're going to qualify, giving designers the flexibility of choosing some options of how they're going to make their building more efficient. And then another change, unfortunately in my mind, is that the way they're applying that to the ERI is that the ERI will also then have to be 5% more efficient, which in terms of the way the ERI score works means ERI score that has to be 5 less than the requirement, so that the same 5% better that was they're attempting to get at with these 5 flex packages will be accomplished even in the ERI or the performance approach. And so this says the same thing, that for simulated performance, you can now in the simulated performance use renewables, which you couldn't before, and you can use renewables, but only up to a certain amount, 5% reduction in energy use. So you can, if you want to use simulated performance, you can count renewables, but only up to a point. So the energy rating index really took a blow in the 2021. We don't even have the option of an energy rating index in Montana yet until the 2018 is adopted. But what they made, the changes they made in the 2021 make the likelihood that people will move in a big way towards the energy rating index option less likely, because they moved the required score from 61 back down to 54, where it was at the 2015 level. And then they reduced that even farther by reducing that down to 51 once you include that the requirement effective by the flex package. So essentially, after the 2021 is adopted in who knows what, we're talking probably 1923 at the state's current rate, that it will be harder to comply per the energy rating index. And it also puts a limit on the amount of renewables that can be counted in the ERI path. The limitation, this 5% limitation, is not currently applicable with the 2018. So in somewhat of a step backwards in my mind, the ERI has been modified in these ways. Most of the folks who are familiar with home energy ratings now believe that builders who would like the flexibility of doing various kinds of trade-offs will more likely use the performance approach instead of going with the ERI approach once the 2021 requirements are actually adopted. And building the 2021 IECC has a zero energy appendix. So in addition to the solar ready appendix, it adds a zero energy appendix that is a combination of ERI score plus renewables to get you to a ERI score, HERS rating score of a 0. Again, it's placed there because the thought is that some local jurisdictions may want to create a zero energy option for their jurisdiction. And of course, if you followed what's going on in California, they're already requiring zero energy on new construction there as of 2020. So while California is out there, California also provides an image of where that could go in the future. I'll also mention that in terms of residential construction that includes, commercial construction that includes residential elements, there's an allowance now in the 2020 IECC that you can comply with building tightness of dwellings that are within a commercial building, which most likely is over 4 stories, over 3 stories in height, by applying Resnet Standard 380 for how to do a blower door. And but interestingly enough, the metric for the tightness of that dwelling unit within a commercial structure is no longer ACH 50, it's in terms of CFM per square foot of exterior envelope, which makes a whole lot more sense. But that's not insignificant because it suggests that perhaps in the future, you could see the residential building tightness metric going from air changes per hour to CFM per square feet, which, if you think about it, I would argue is a more reasonable approach. That is the last slide. Is there anybody who have final questions or any discussions? But certainly, I would say I deserve a cupcake for coming close to 2 o'clock. Any questions?
Thank you for putting this on. I appreciate it.
Okay. So Carl, will the video of this be available online? What will be available online? Do you have an idea?
I hope to make the video available, the recording of this available, and a PDF of your PowerPoint presentation available to
Right.
folks. And I'll try to send out a link to all that as soon as we get it all posted.
Great.
You're getting a lot of thank yous. So not any other questions in the chat other than what does NCAT stand for, and Victor for that. So.
The new cats for appropriate food. No, appropriate. I can't figure out the T, but anyway, no, it's the National Center for Appropriate Technology. We've been around since the mid-70s and involved with energy efficiency and sustainability, agriculture sustainability. So we've been around and involved with low energy sustainable buildings for a long, long time. Check us out on our website. Okay, no other comments? We'll let you go. Carl, any closing thoughts?
I don't think so. Thank you, everybody, for sticking in there. It was kind of, these are long presentations. They were meant to be long at the original conference, and so seems like everybody was active, and we appreciate it.
Okay, let's hope that in the future these can be in person and at the Building Codes Conference.
Absolutely.
Okay, best wishes for everybody.
Thank you all.